Welcome aboard, welcome aboard, welcome aboard. This is your Captain Shreyas on the PWJ English channel. And today we are doing electromagnetic induction. Let me tell you, this is the same concept which makes the... This is your Captain Shreyas on the PWJ English channel. Yeah. So this is the same concept behind the working of an electric guitar. You might have seen it in movies or maybe used it. Maybe some of you are already guitarists. So the way the electric guitar works has the concept of electromagnetic induction, and these wires are metallic. There is a pickup out here, and there is a whole lot of process. This page, it's quite insightful, technical. If you are fond of electronics, modeling and all of that, then you can go through this, which talks about how this person has designed this and modeled this particular electric guitar. All right. Anyways, we don't have to go into those details, but we know it is the working principle of an electric guitar, the concept of EMI. So that's what we are going to study today. We're going to solve questions. We're going to solve PYQs within the session. And then we are also going to apply these concepts and also study these concepts right from the scratch, right from the basics, covering every aspect for JEE mains as well as advanced. If you talk about JEE advanced, there are certain concepts which are extra, which are not there in mains, like LR circuits, right? And even the concept of time varying magnetic fields producing electric fields. All these minor things are there which are extras for JEE advanced. So we'll be doing that also in this particular session. Okay, so shall we begin, my dear warriors? Are you ready? Are you excited? Are you thrilled? How is the Josh? Let me know quickly in the chat box right away, right now. Perfect. Let's begin then. Okay, so let's understand the first concept, and that is basically Faraday's law. But before that, why this Faraday law comes and what is this whole concept of electromagnetic induction, let us understand in small detail. See, we have noticed that if you have a charge, right, then that particular charge is going to create something called as electric field. We have noticed this charge which is going to be at rest creates electric field, But if this charge begins to move in a wire, so if you have a wire carrying current, so this is basically moving charge, which is nothing but current, then that current ends up producing magnetic field around it. Is that right? It ends up producing magnetic field around it. Oersted demonstrated this by sprinkling iron filings around the current carrying wires. So moving charges inside those wires create magnetic fields around those wires. Similarly, we all noticed that if you have an electromagnet or basically a bar magnet, let's say something like this, we have a bar magnet, something like this. This has a north polarity, south polarity. It could be even a horseshoe magnet. This particular bar magnet ends up producing magnetic fields around it. It ends up producing magnetic fields around it, something, let's say, like this. I'm just showing few of these lines. There would be obviously many more such lines out here. So it ends up producing magnetic fields around it. So this is a magnet at rest. A magnet which is at rest ends up producing magnetic field. So the next obvious question should be, if a stationary charge can produce electric field, but moving charges in a wire produce the other kind, which is the magnetic field. So same logic being applied. If I have a stationary magnet, it is producing magnetic field. So if I make the magnet move, shouldn't it produce electricity around it? And the answer is a yes. So if you take a magnet or anything which is magnetic, it could be even an electromagnet, guys, it doesn't matter. So if you take any kind of magnetic body, but now it is in motion. So when you have a magnet in motion, not only does it produce its own magnetic field, but also it produces around it the electric field. So now the entire picture is complete, and now you will understand what this chapter is all about. This is the main agenda of this chapter. This was there in the first two chapters of your NCERT, or if you look in H.C. Verma, it is slightly different chapters, right? So the concept of electric field for stationary charges, electrostatics and Gauss law. This concept is there in the chapter of magnetic field, magnetic effects of current, right? Which is Biot-Savart's law, Ampere's law, Orsted's experiment, etc. This is for magnetism, where pure bar magnets or just electromagnets, like even solenoids, end up producing magnetic fields around it. Now this is the last missing piece of that puzzle, which completes the entire unit of electromagnetism, where moving magnets end up producing electricity. And that is what Faraday ended up finding out. And in fact, that was his intention also. He wanted to see if moving magnets can produce electricity. See, usually what happens, discoveries, inventions happen accidentally. But when Faraday tried to find it, although it was a kind of an accident, his thought process was exactly this, that if these three are there, even this should be there. So in his laboratory setup, he tried all sorts of things to take a magnet and figure out if it can create electricity. He used strong magnets, he used different coils, he placed the magnets within the coils, he moved those coils, he did literally everything possible. But he was not able to generate electricity. But one fine day, it so happened that his apprentice, his volunteer worker, whosoever, he was doing something, and suddenly the voltmeter, which hadn't moved even an inch for so many days, suddenly flipped and it moved. And that was a big shocker for Faraday, because he was so excited and happy and puzzled that how come this needle, which hasn't moved for so many days, suddenly moved. And then he questioned that apprentice that, what did you just do? He said, nothing, I just moved this magnet, I just moved this coil. Then he started to wonder, why is it that when I was moving, this voltmeter never moved? Then he understood that during those times, by the way, things were pretty huge. Nowadays we get everything in small sizes, right? So by the time he had moved the magnet, or by the time he had moved the coil, and he came back to see the voltmeter reading had already gone back to zero. So it only existed for a small amount of time and it came back to zero. So by the time Faraday came back from his setup, the reading was gone. Then the idea clicked for Faraday. So it was never placing that magnet inside the coil or moving that coil. It was always about how quickly you are changing it, how quickly you are moving the magnet, how quickly you are moving the coil. That was determining the electricity, and it only lasted as long as you were changing it. The moment you stop changing, because once you leave the setup and come to see the readings, nothing is changing, the reading also vanishes. So there was a time gap because of which he was not able to see. But if you had two people, one performing that change and one taking the reading, then you could see that only when the person was changing something in the setup, there were readings shown. Otherwise, no matter what you do, there were no readings shown. So that's why Faraday was able to formulate his law, which says that changing of magnetic flux produced electricity, and how fast you changed it determines that EMF, and it is exactly proportional to it. So, the induced EMF, which is basically the electricity generated, in a coil is directly proportional, to how quickly you are changing the magnetic flux. That means the rate of change of magnetic flux, So he mentioned that if the magnetic flux is constant, then there is 0 volts of induced EMF, but the moment magnetic flux changes, you will see that there is induced EMF. There is induced EMF in terms of some volts. How much that volt is determined by how quickly that magnetic flux is changing. So this was the main conclusion from Faraday's experiments, which went on for a long time. But one small accident, or you can say small mishap, which was done by his apprentice, led him to actually figure out how it happens, and he was able to see that it is the change of the magnetic flux which is causing the induced EMF. But I know what you guys are thinking. Sir, what is this magnetic flux? First you tell me that. I know. No worries. Let's talk about what is magnetic flux first, and then let us actually write down the formula. Alright? Okay. Yes, Techno, this is a detailed class. Hello, Divit. Hi, Shri. Welcome aboard. Hi, Uma. Alright. Magnetism and matter chapter is not deleted, man. It is there. It's a very, very low weightage chapter. That's all. Okay. Hi, Ravi. Good evening. Hi, Satish. Good evening, my dear. Everyone. Great. Now, let us see what magnetic flux actually means. Say, for example, if you have some kind of a surface, let's say something like this. This particular surface may have some magnetic field lines passing through it. So let's say those magnetic field lines which are passing through it are something like this, maybe. I'm just taking some random magnetic field lines, guys. Doesn't matter how I draw them. These are the magnetic field lines. Now there will be also an area vector for any surface that you choose. This is that area vector for that particular surface. If this is my surface which I have imagined, or it could be an actual, this is my surface area vector which is always perpendicular to that. This is your magnetic field B. The magnetic field and the area vector will end up making some kind of an angle. I will call it theta, the angle between magnetic field and the area vector. So then my magnetic flux, whose symbol is phi, you can also put B to specifically say that, listen, it is from magnetism, or you can just leave it as phi for now, because we know we are discussing magnetism only, we are not discussing electric flux. But most of the books will use this symbol B, or they will just write phi mag, means it is magnetic flux, just to differentiate the phi of electric flux and the phi of magnetic flux. So that flux will be nothing but the dot product of the magnetic field, into the area vector. So dot product means each vector's magnitude multiplied with the cosine of the angle between them. that will become your magnetic flux. This definition is exactly identical to electric flux. Instead of magnetic field, you had electric field in the chapter of Gauss's law. So just like electric flux was electric field dot producted with the area, here magnetic flux will be magnetic field dot producted with the area. So electric flux is E dot A, magnetic flux is B dot A. That's it. That's the only difference. Unit wise, it goes like this. B has a unit of Tesla. Area has a unit of meter square. The flux has a unit of Weber. What unit does it have? It has a unit of Weber, guys. Alright? This is absolutely clear. So 1 Weber is 1 Tesla meter square. Sometimes you might have seen magnetic field, instead of writing Tesla, they write meter square below the Weber. So Weber per meter square. So that is also perfectly fine. So a Tesla is also, you can see Weber, the short symbol is WB, divided by your meter square, guys. Alright, this is also perfect unit. Okay, so magnetic flux tells me how many lines are piercing through an area. If more magnetic fields pierce through that area, the flux is larger. If no lines pierce, then there is no flux. If there is less lines, then there is less flux. So lines piercing through an area is basically conveyed by your magnetic flux. Okay, I hope this is clear. J. Davy, I will probably discuss that maybe someday in some other session. Sir, you want sessions for Erodo and other books also? Definitely, I'll be conducting them very, very soon, man. Okay, very, very soon. JEDV, don't worry. All right. Now, if the surface is curved, then what do you do? Say for example, this is my curved surface. I have taken some random curved surface, something like this. And here the magnetic field is also different at different places. So what you do then is you take a small patch, and that particular patch will have a small area vector popping out, something like this. That small area vector will be dA. So this is my curved surface. The dA happens to be a small elemental area that I have chosen. In that small patch, there will be some magnetic field which is passing through it. So let's say that is B vector. So there will be a small flux through that area. So the small flux through the area, small area, that will be also d phi, and that d phi will be the dot product of the magnetic field with that small area vector. Instead of B dot A vector, it will be B dot dA. That's the only difference. Is that right? So phi will be B dot A, d phi will be B dot dA for that small area. So the total flux, therefore the total magnetic flux must be the addition of all the fluxes through all such small elemental areas through that surface. So the total flux will be addition means integration. So integration of d phi. Therefore, I can quickly say phi is equal to integration of magnetic field dot producted with the small areas at every single place. Is that right? So this is how you can calculate the magnetic flux over a curved surface. For a flat surface, uniform field, it is very simple. You just use this formula. So this formula usually works for a flat surface with uniform field, and the field should be uniform, and magnetic field should be uniform. But the moment magnetic field changes or the surface curvature changes, then you are forced to use integration, none other than that. Now, yes, Divit, whatever is your doubt, please let me know. If it is related to the topic, I will help you. But something else, definitely I'm going to have more gupshup sessions. I know you guys enjoyed the last time's war, but I'll get more sessions where you understand how to prepare, strategies, everything. Okay, we'll have a gupshup. Maybe we'll try it tomorrow itself. Why not? Okay. Now, I want you to understand one more important thing over here. If by chance somebody decides, I want to take a closed surface, okay, I want to take a closed surface, something like this. So this is our closed surface, visualize that. So this is a three-dimensional surface. It could be anything, guys, of any shape, it doesn't matter. Right now, this is our three-dimensional surface. Through that, there could be magnetic field lines going out, there could be magnetic field lines coming in, magnetic field lines going out, magnetic field lines again coming in. So many things could be happening at different places. But I know one thing for sure, magnetic field lines are always continuous loops. So no matter what, whichever line enters inside this 3D surface will have to come back again, because they are always going to be closed loops. Do not forget that. So magnetic field lines being closed loops, whatever line exits out will have to enter, whatever line enters will have to exit out, because they are closed loops. So magnetic field lines are always closed loops, magnetic lines, magnetic field. Hence, even if I try to find the magnetic flux for such a closed surface, 100%, the answer to that will be always 0. Because whatever flux goes out will also come in. So flux going out is always positive, flux entering in is always negative. This is the sign convention, in case you have forgotten, for Gauss's law. Whenever flux goes out, flux coming out, like say over here, is always considered as positive flux, and anywhere the flux enters inside, it is considered as negative flux. So how many our lines exit, meaning the positive flux, will be exactly the negative flux, because that many lines will have to enter back. So that is why the positivity being negativity, the total flux for a closed surface is 0. So you will see, if I try to integrate the magnetic field at every single place with the small area vectors at every place, you will see the answer for such a number or integral will always be 0. This is also called as Gauss law in magnetism. Gauss law in magnetism. Notice some similarities and some differences. In electrostatics, try and recollect, it was cyclic integral. Oh, by the way, I should put cyclic integral here because it is a closed surface. So that symbol is very necessary, or else it will just mean an open integral means open surface. So there could be leakages. So we want a closed surface here. So E vector dot dA vector was always net charge inside by epsilon naught. This was Gauss law in electrostatics. This was Gauss law which was there in electrostatics. See some similarities and see some differences. Expression looks very much similar. Left hand side is the total flux. Cyclic integral is there. Dot product of the field vector is there with the area vector. Just that the field has changed. Here it was electric field. Here it has become magnetic field. For electrostatics, you used to get some expression on the right hand side, which is the total charge inside that surface by epsilon naught. Why is it that I have got 0? Because I know, okay, whatever lines goes out comes in. But there is another way of looking at it. That is, if by chance I do not consider it as 0, if I just think of it as magnetic charge inside by whatever permeability or whatever it is, then the magnetic charge which is there inside will end up being 0. Meaning the amount of north poles inside will be exactly equal to the amount of south poles. Because this represented charge, in electrostatics that will be electric charge, in magnetism it would represent magnetic charge. Which means the right hand term being 0 says that the magnetic charge is 0 inside. Which means the amount of northness and the southness polarity wise is same. That means they are dipoles. Their polarities are present equal in amounts no matter what surface you take. That proves the fact that in magnetism, you will see that there is no monopoles. The polarities are always as dipoles. You can never buy a single pole in the shop saying, please shopkeeper, give me a north pole. Hey bro, please give me a south pole. They will slap you. It's illegal. It's not allowed. It is not possible. If you buy a north pole, you have to buy a south pole. If you buy a south pole, you have to buy a north pole. There is no negotiation in that. You cannot cut a deal saying, I just want a south pole. Is this absolutely clear, everyone? Pakka? Understood? So this is the proof, or you can say this is the expression which says why magnetic monopoles do not exist. So magnetism exists as dipoles. So I'll just briefly mention it. Monopoles do not exist. So magnetism only exists like dipoles. This is the law saying that, Gauss's law in magnetism. We have discussed this before also in magnetic field chapter, but this is again, recollecting the same idea. Anyways, now that we have understood what magnetic flux is, we will never take closed surface because we know for a closed surface the magnetic flux will always be 0. So most of the times you will be dealing with open surface. This is a curved surface, but it is not closed. Rather, I will say it is a open surface. So for such an open surface, you will always get some flux like this one or even this one. This is also a surface which is also open. It's not closed from all the sides. So that's why we will be dealing with fluxes coming only from open surfaces for checking out Faraday's law. Just to give you an example, let's see whether you get this. Say we have a surface like that. This has a radius of, let's say, r, and let's say there is a magnetic field which is going like this. This magnetic field happens to be, example, 0.02 Tesla, and let's say this particular radius happens to be 0.1 meter, and it is told to you that this magnetic field is making some angle with the plane of that particular surface or that coil. And let's say, Chumma, we can take this, as 30 degrees. Okay, we can just Chumma take it as, let's say it is 30 degrees, whatever this angle is. So can you figure out how much flux is passing through that particular loop? How much magnetic flux is passing through that particular loop? Okay, so let's figure that out. First of all, the formula for magnetic flux, let me decide. Since it's a flat surface, as you can see very easily, it's a flat surface, guys. So that means I will have to use simple dot product of the magnetic field with the area vector. So I'll just use BA cos theta. How much is the magnetic field? It is 0.02 Tesla. How much is the area? Oh, area I do not know, but I know it is pi into r square. Radius is 0.1 square. So that is your area vector's magnitude. Pi r square is the area. Radius was given to be 0.1. The last thing is cos theta, and this is where most students generally make a mistake. They take theta as 30. No, be careful. Theta is always the angle between magnetic field and the area vector. So if you notice how the area vector will come, the area vector will come out to be like this. So the real angle that you will need to take is this angle, and it will not be 30, my dear, it will be 60 degrees. So it will be technically cos of 60 degrees. Got it? So this is the most common mistake which generally students make. So this will become 2 multiplied by 10 raised to negative 2. This will be pi multiplied by 0.1 square is again minus 2 power of 10. Cos 60 is obviously half. This number 2 and 2 will cancel. So I will get pi multiplied by 10 raised to minus 4. But this will be in Weber. So I have an idea. I can write it as 3.14 multiplied by 0.1 into 10 to the power minus 3 Weber. Deliberately I have split negative 4 power into minus 3 and minus 1. So this will be 0.314. This is milli. So milli Weber. So 0.314 milliweber is the final answer for the magnetic flux. Is this clear? How to solve this? Ananta, no, dear, I'm not teaching. No, how can I be everywhere? Yes, I did mechanical engineering. And yes, Padma Priya, you can crack JEE even if you start now. And what do you need to do to make it possible? There are multiple ways you can achieve it. First is planning. First is deciding your targets. Then deciding what books, what lectures you are going to follow, how you are going to follow, decide what is high weightage, what is low weightage, and target either mains first or second attempt based on whatever is possible for you. And then once you have a plan set in mind with all the resources and what you're going to do, then just follow it. You will achieve it. So you need to just follow a plan. That's all. Okay. Yeah. Great. Thank you. Thank you, little stars. All right. Yes, Divit, whatever doubt, let me know if it is related to the topic or JEE. I will definitely help you out. Great. Now that we understand what magnetic flux is and how it has to be calculated, let's come back now to our main agenda, which is our Faraday's law. And Faraday's law said that whatever electricity is being generated is proportional to how quickly this flux changes. So let's write down the actual formula for this. So let's write down the actual formula for this. So the actual formula for Faraday's law will look something like this. So the EMF induced symbol is E. I can put a subscript I and D, and I am only interested right now in the magnitude of it. It is proportional to rate of change of magnetic flux, which is d phi by dt, I am only interested in the magnitude, guys. So I am just putting mod over here. So if I put equality in proper SI units and if I define it properly, then I will get this as just nothing but E is equal to d phi by dt. Just like F is equal to MA, F is not equal to KMA or 3MA or 0.7 MA. It happens to be just MA in SI or CGS units. Same way, if you use SI, CGS units, standard units, you will get it to be equal to, else you might get some number as a constant just for the conversion factor. We do not worry about it. So right now, our induced EMF is just d phi by dt. The electricity produced is the rate of change of magnetic flux. Now, if that is the scenario, let's understand it with a diagram first, and I will also show it to you practically, don't worry. So I'm taking a coil, and I'm showing two different instances of that same coil. Notice what's changing. Let's say this is our area vector over here. Let's say earlier there were some magnetic field lines piercing through the coil. After some time, you saw there were suddenly more magnetic field lines piercing through that same coil. So the flux has changed clearly. Can you see that? In this particular coil, earlier versus now, the flux has changed. So there is a change in flux, so there will be EMF which will be induced. So you will see suddenly this particular coil if you measure the voltage, it will show some E voltage, the same voltage, and that E voltage will be how quickly the flux has changed, the rate of change of it. Okay, that is what Faraday's law means. Let me give you a simple example to make you understand this. Say, for now, there is a coil like this. It has an area, ready-made, we can take it as 0.1 meter square. This is also 0.1 meter square. Right now, there is a magnetic field which is piercing through it. And let's say the magnetic field is 0.2 Tesla. Within some time, it so happens the magnetic field changes. Let's say now it becomes I don't know, maybe I will just take it as 1 Tesla. And this change happened in let's say 0.2 seconds. So definitely I can say now the magnetic flux has changed. The magnetic flux has changed. Therefore, I will say there is an induced EMF in that coil which we are talking about. There will be definitely some kind of EMF which will be there in that particular coil, and we can figure how much that induced EMF is using Faraday's law. So by our Faraday's law, since EMF is equal to d phi by dt, my dear, here this EMF will be how much my flux has changed upon the time interval. So it's not an instantaneous change, it's a big change. So I can put final flux minus initial flux divided by how much ever time it has taken. My final flux, field multiplied by area, because flux is B dot A. Here B and area vector are in the same direction. Notice this particular arrangement, guys. Area vector is exactly over here. So theta is 0. So if theta is 0, cos of 0 degrees is always 1. So when I take the dot product also, I will just get it as 1. So magnetic field is 1 and area vector's magnitude is 0.1 into cos 0, which is also 1. Again, next time, initially, if you notice, magnetic field is 0.2, area vector is 0.1 and cos 0 is still going to be 1 by the time interval, which means it is 0.2 seconds. So this will be nothing but 0.1 common, I can take it from both sides, 1 minus 0.2, whole thing divided by 0.2. Decimal places can be cancelled, so I will be left with 1 by 2 and this will be nothing but 0.8. So this, my dear, will be 0.4 volts. That's the answer. So the induced EMF in that particular coil will be how much? It will be 0.4 volts. Clear, everyone? Yeah. Now let's say this same coil had some resistance. This same coil also has some kind of resistance in it. Can we figure out how much current is flowing in that coil? Can we figure out how much current is going in that same coil? The answer is yes. We can also figure out how much current is going. So for figuring out how much current is flowing in that coil, I need the resistance. And let's say the resistance of that particular coil is given to be, take something, I don't know, I will take it as maybe 4 ohms. Maybe 4 ohms. Okay. Then using Ohm's law, we can say, so by our Ohm's law, we can say the induced EMF is the current which will go in the coil multiplied by the resistance of the coil. So the current within that coil will be the EMF which is induced divided by the resistance of the coil, which will be, induced EMF is 0.4 volts. Okay, the resistance of the coil is 4 ohms. So this will be 0.1 ampere. So this will be 0.1 ampere. Great, sir. I understood this also. Sir, can we also figure out how much charge will go because that current will flow in that coil in that 0.2 seconds? Yes, why not? We can even figure out how much charge will go, because see, there is a voltage which is created. Because of that voltage, there will be some current, and because there is some current, in that time, there will be some charge which is going. I know what you are thinking, we can just multiply current multiplied by time, we will get the charge. That's right, provided we knew the current. Let's say I had not given you this question. Let's say I had not even given you this question. I had directly asked from here, how much charge is flowing? As an independent question, without knowing the current values, etc. Then how would you do it? Then my logic will be, the induced EMF was, let's say it was d phi by dt. Let's say it was d phi by dt. I will say induced current will be the induced EMF divided by the resistance of that coil. So induced EMF is nothing but d phi by dt, and then the resistance of that coil is over here. But what is current? Current is how much charge, dq charge, is flowing per unit time. Current is nothing but charge flowing per unit time. Clearly we can see that this dt and this dt will end up cancelling out. So therefore, I will get dq is equal to, notice, d phi divided by the resistance of the coil. That's enough for me now to figure out how much charge is flowing. So I can now say confidently that the charge which will flow will be how much is the change in the flux, magnetic flux, upon the resistance of that coil. The change in the flux we can easily calculate. Field multiplied by area, which is 1 multiplied by 0.1, minus field multiplied by area, which is again 0.2 multiplied by 0.1, upon resistance of the coil is needed. The resistance of that coil, we had taken it as 4 ohms. Okay, so if I put it over here, we will get the answer. So 0.1 is common, my dear, and we have 1 minus 0.2, whole thing divided by 4. So this will be 0.1 multiplied by 0.8 divided by 4. So 0.8 divided by 4 is nothing but 0.2. So we will have 0.1 multiplied by 0.2, which is 0.02 coulomb. So the charge which will flow is 0.02 coulombs. Yep, everyone? All right. Sir, can you just tell me 30 degree and 60 degree what you explained? Not all math steps can you explain? Satish, in that previous example, I just said that if this is the coil, the area vector will be like this, magnetic field is like this, the actual angle between them is this angle. But in the real question, what was given to me was, what is the angle made by the field with the plane of that coil, which is right over here. So that is why we had no other option but to figure out, okay, if this angle was given, how much will be this angle? So that came out to be 60 degrees. Rest of the things are very simple, where you just substitute one by one. Here area was just pi r square, right? Area I have just used pi into r square. Magnetic field was directly given, and theta I put it as 60 degrees. Rest all is simple maths. Cool? Okay. Now I have another question for all of you. Let's say in the same problem, what I did is I made n number of windings. Let's say 3, 4, 5. There are some windings of that coil. Okay, there are some windings of that coil. That means there are some turns which I have made for that coil. So this coil has some turns, something like this. And let's say I tell that there are 3 turns for that coil. 3 turns for that coil. What do you think will change in this entire problem? These magnetic field lines will pass through every turn and will add up to the flux. So when you have a coil, the magnetic field lines will pierce, and another turn will again pierce, another turn will again pierce, another turn will again pierce. So every turn it pierces adding to the flux. So if there are n number of turns, it will create n number of times more flux, which means the change will also be n number of times larger. So everywhere you will see, because this extra number 3 turns came, you will notice when I calculate the total flux, I will have to also multiply this with 3 and this with 3. Is that making sense? The total flux of all the coils together, final flux will be multiplied by 3, multiplied by 3. So that means even this number 3 will come out to be common over here as well as over here. Hence the induced EMF will be 0.4 into 3, which is 1.2. So 1.2 volts will be the new answer if there are 3 turns. If there are n turns, it will be into n. So that's how you factor in the number of turns of that coil. Is this clear, everyone? Yeah. I'm happy to tell you I made it into IZ or TVM with rank 647 in IIT, and your one-shots and problem solving series helped me a lot. Oh my God, I'm so grateful, man, and thankful that you came back over here and told this. And like I have been telling this every time, one student at least comes back in every session of ours and is telling us about their achievements. And Harish has gone into IIT ISER, guys. He has cleared ISER aptitude test, and he's making it really big in life. He's going to do research. It's a very intense institute, very renowned, very popular, very, I would say, respectable degree that you are going to get. Many kids even leave IITs for getting into ISER, and you have got an all India rank of 647. Very good, congratulations, and may you do really, really well, man. Okay, and I hope this inspires every other student watching this video, whether live or recorded. Right. So we have understood how do we really calculate and use this expression. Rate of change of flux, final flux, initial flux, take the difference, and then you are sorted. But sometimes the flux could be directly given to you. Sometimes the flux could be directly given to you. So what do you do in those cases? Say for example, something like this. Let's say the flux is already mentioned, or let's say it's mentioned that you have an area of 2 meters square and a perpendicular field of point, or let's say 7t cube plus 2 Tesla through it. Can you figure out the induced EMF, the EMF which is induced at t is equal to 2 seconds? That kind of question. Kind of derivatives based. So let's visualize what is really happening. You have a coil, and that coil has some area, that's okay. But perpendicular field means perpendicular to the area. Now many people feel, sir, perpendicular means theta is 90. So cos 90 is 0, and many people end up writing that the flux is 0, which is a big mistake. Guys, see, it is perpendicular to the area but not the area vector. The area vector is still here. Do not forget that. So this is the area vector. Yes, the field is perpendicular to the surface, but it is parallel to the area vector. So technically theta is 0. That means cos of 0 degrees is still going to be 1. It is having some value. So we can actually find out how much is that flux through that particular coil, and that will be B A cos of 0. B is this number, which is 7t cube plus 2. Area is 2, cos 0 is 1. So this will be 14t cube plus 4 Weber. That is the flux through the coil. But that is not the question. The question is, what is the EMF? So the induced EMF formula by Faraday is the d phi by dt. I am interested only in the magnitudes. So I need to differentiate this particular equation. So I will take that number 14 I will take t cube plus I will take 4 and I will differentiate this. 14 is a constant number, take it outside. So derivative of t cube alone is enough and derivative of 4 separately. T cube's derivative will be 3t square. d4 by dt is a constant, so 0 is the answer. 14 and 3 guys, that's 42, and then you have t square. That is your induced EMF, how it changes with time. I've got a very generic expression in terms of the time that we have over here. Is this fine? But that is not what we want. We want at 2 seconds. So the induced EMF at 2 seconds will be obtained if you substitute the value of time as how much? 2. So I'm going to substitute the value of time as 2 seconds because that's when I want how much EMF is there. Every instant the EMF is changing because it's a very weird magnetic field which is changing. Alright, so 42 multiplied by 4 guys, that should be your answer. Understood? 42 multiplied by 4. How much is it? 44 is 160, 2 4s are 8. Yes, so it will be 168. 168, what is it? We are finding EMF, right? So it will be volts. Yeah. So the EMF will be 168 volts. Not Weber, man, it will be volts. Don't confuse. Weber is for flux. So this will be Weber. When we are finding EMF, Weber with time will give you volts. Okay? Great. Understood till this point? Shall we go ahead to the next? So we have seen how do we calculate EMF for different scenarios. We started off with a coil, we changed the flux and we figured out currents also, we figured out charges also. We saw what to do if there are n turns also and what to do if there is a varying magnetic field also. Sometimes what will happen is your loop will change its area. That kind of question is also there in JEE, NEET, Advanced. You take any exam, most of the times this question you would have seen it. Kind of confusing. You have, let's say for example, a square and the side of that particular square, let's say is, we will take it as 0.1 meter. Chumma I'm taking, okay, 0.1 meter square. And right now, there is a magnetic field which is passing through that square, something like this. And let's say the magnetic field, let me keep it a simple value, let me keep it 2 Tesla. What you do is, you suddenly stretch the square, so immediately all sides are being pulled everywhere. And now that square has become circle. Now it has become circle. The magnetic field is still the same, but notice some of the field lines might end up escaping outside also. So the flux might change. I don't know whether it will increase or decrease. It depends on the size of this circle. If those field lines are inside, then yes, the flux will increase. If the field lines go outside, then the flux will decrease. It depends. So first, let's figure out what exactly happens when you convert a shape to another shape. So from that we'll understand whether flux is increasing, decreasing. From that we can figure out how much is the electricity produced. Let's say this change happened in 0.1 seconds. Very quickly, it was a square, you pulled it within fraction of a second. 1/10 of a second we have done it. Yeah, modern physics will be doing later on, man. First let me finish electromagnetism. Without that, going to modern physics is not right. Okay. So what we do is, we say from this side to this side, the perimeter should be the same, isn't it? Perimeter should be the same, length of the wire. So perimeter is the same, so the length of that wire is going to be the same. So if that is the scenario, what is the length of the wire here? It will be 0.1 multiplied by the 4 sides. Here there could be some radius, I will call it as r. It will be 2 multiplied by pi multiplied by r. Great. So how much is my r going to be? 0.1 into 4 is basically 0.4. 2 and pi can go below this number. So it will be 0.2 divided by pi, which I can write it as 2 by 10 pi, or basically 1 by 5 pi. 2 by 10 is 1 by 5. So a radius is 1 by 5 pi meters. I have not substituted pi. As of now, we will see what to do with it later on. We'll see. Now from this radius, we can figure out the area afterwards also, and we know the area before also. So we can find the change in area. So now I will say the change in the area, which is delta A, will be area of a circle, which is pi r square, minus area of a square, which is the side square. Here our radius is 1 by 5 pi, notice. So I'll just put 1 by the number 5 pi and square it, minus the side square, meaning just 0.1 square. Let's see what do we get. Pi divided by 5 square is 25. So 25 pi square minus 0.1 is 1 by 10. So 1 by 10 square is 1 by 100 basically. We can take some LCM like this, 100 pi square maybe. So in such a scenario, I will have to multiply this number with 4. So this will become 4 pi minus, actually forget that. First we'll cancel off pi. Let's get rid of pi. So this will be just nothing but 1 by 25 pi minus 1 by 100. Is that right? So you can write this as 100 pi with the LCM. This will go 4 times and this will go basically pi times. So that will what your area change be. Now this is coming out to be positive number. That means the area is definitely increasing. Area is definitely increasing. So this circle has a larger area, which makes sense. Whenever you convert any random shape into a circle, the circle is always having the largest area for that given perimeter. That's okay because 4 is more than pi. Once you know the change in area, we can find the EMF. EMF was how much is the change of flux divided by the time interval. Now we all know flux is nothing but B into A. B is a constant. B, magnetic field, was never changing. It was only the area which was changing. So B taken outside. So I am left with delta A by delta T. I can just shift this B outside like how you shift in derivatives. So now we know what that delta A is. From here, we know what the time is. We also know how much is the field. The field is nothing but 2 Tesla. The time interval is 0.1 second. And the change of area is 4 minus pi divided by 100 pi. Is that right? So this will become 20 by 1. So this can be written down as just 20 multiplied by 4 minus pi, whole thing divided by 100 pi. 20 by 100, that's 1/5. Okay, so you will get 4 minus pi divided by 5 pi as the EMF in volts. That is the answer. If you substitute, you will get the value in decimal. Clear, everyone? Yes, Anirudh, you can definitely watch my older classes, man. Watching live recorded, it's up to you. It's up to your own choice. It's nothing like you have to watch live, you have to watch recorded. It's completely up to you. But watch. That is more important. That is the most important thing. Students are asking wrong questions. Can I watch you recorded or live? It's okay. You watch me recorded, fine. You can still get into IIT. You can get IIT JEE Advanced. You can crack it. Anything, any institute you can get. But watching me is more important than anything else. Cool. All right. So area changed. In this problem, magnetic field was not changing. So that's why I brought magnetic field outside. And I said rate of change of area over here. Area change we calculated simply by geometry, nothing else. And substituting, we got the answer. So in this question, area was changing. In this question, magnetic field was changing. So now you might be wondering, sir, are there different ways of changing flux and creating electricity? Exactly, you have hit the nail. See over here, when I said flux is BA cos theta, And I also mentioned that Faraday's law says that whenever flux changes, if magnetic flux is changing, there is electricity which is created, this second line, which means there are multiple ways of changing the magnetic flux. One way is you change the field. Another way, you change the area. Third way is you change the angle. The recent problem what we did, from square to circle, we have changed the area. The previous problem which included derivatives, we were changing the magnetic field. That's why the flux changed. So the only scenario left to discuss is, can we have changing theta and thereby create create an induced EMF, create change in flux? The answer is yes, and let's see how do we do that. Is that clear? So we have discussed changing B, changing A. Now the last thing left to discuss is theta, then we can move ahead. So let's see that. All right. For that, rather than giving you a problem, it's actually a theory pointer only. So imagine this. This is your coil. This is your coil, and this particular coil, let's say, has n number of turns. This particular coil has n number of turns. It has some area vector A like this. And what happens is, it is making some angle with the magnetic field. It is making some angle with the magnetic field. Let's say the magnetic field is right now over here. And the magnetic field making some angle theta like this. Because I just mentioned that this coil will have to change the angle, because that is the third case which we are discussing. Theta has to change. So the coil will have to rotate in some way or the other. So let's just assume that, okay, this coil is probably having some kind of a axis about which it is rotating. Maybe this axis is like this, and right now it is rotating about that particular axis with omega. So that is its angular speed of rotation, omega. So that particular coil is spinning like this. Can you see that? This is that axis. It's spinning about that axis. Because of that, what will happen? The area vector will keep changing its direction. Right now area is here, then it will be here, then it will be here. So the angle obviously is continuously changing. That is what we wanted. In fact, now we can write theta as omega into t. We know angular displacement is omega t. So theta is how many radians per seconds multiplied by the seconds will give me the radians that I am sweeping with respect to the magnetic field. So I can easily say the flux phi will be magnetic field, which is B, into area into cos theta, but there are n such terms, so do not forget to multiply this entire thing with n. But my area is making some angle which is changing, and that angle we just wrote it as omega t. So phi is BAN cos omega t. Now using Faraday's law, we can say EMF magnitude wise is d phi by dt. Magnitude wise is d phi by dt. So if I substitute the value of flux in this equation, how will it look like? B, A and N are all constants. So just bring them all outside. B, A, N is outside. What is left inside the derivative is only this term cos omega t. So I have to take the derivative of cos omega t. Making sense, everyone? Yeah? Alright, great. Now, what we are going to do, put BN as it is. Derivative of cos is negative sign. I'll put that minus sign. So this will become minus sine omega t. But this omega will also come outside because of chain rule. And you will see BAN omega sine omega t. But we were more interested in the magnitude of it. So if I am more interested in the mod value, you will see it is BA omega N. So I will just mention over here, neglecting this, neglecting the negative sign, neglect negative, because we are not interested so much in these signs and all of that. It will be BA omega N sine omega t. BA omega N sine omega t. In this term BA omega N is a constant. This particular term is varying with time, so it is oscillating. It is oscillating. This is looking like a sine equation with a constant outside. Meaning, if I try to draw the graph of EMF, actually speaking, if you neglect the negative sign also, okay. If you don't want to neglect, fine sir, no issues, we will not neglect it, put minus sign. What is the difference? It's just that it will start from below instead of starting from the top. So, point is that this is a sine function. So, it's a negative sign. So, it will go like this, like this, like this, like this. It's a sine function, and the height of this function, the height of this sine function, either this way or this way, is, my dear, BA omega N. That is basically your amplitude. And this wave tells me that sometimes my EMF is negative, sometimes it is positive, which means sometimes the voltage is one way, sometimes the voltage is other way. So the voltage is changing the direction, which means it is a alternating current. Alternating current, my dear warriors, it is AC current which is coming into your coil. So if you take a coil and keep on rotating it inside a magnetic field, you will see it will undergo cyclic process, and in that you will notice the EMF generated is BA omega N sine omega t, where this BA omega N is nothing but your amplitude of the voltage. Sine omega t is a time varying term, and it is nothing but a AC current which is being generated. This is actually the working principle of a generator. In your turbines, wind turbines or hydroelectric plants, thermal plants, etc., you will always see there is something which is rotating. That rotating thing is either a coil or a magnet, and because of that you will see you will get a electric current or a electric voltage in the form of a sine. So this is how actually your current that you get at home, your voltages that you get at home, is being generated at the power station. Is that right? And I will show it to you. Look at it. First, let's have a look at Faraday's law. Very interesting diagram. So here let's take, where is the, no, I want the electromagnet. This is this one. See, I take this bar magnet. You can see there is a magnetic field around it. If I keep it, no matter where, there is no electricity which is generated in that coil. And one way to see whether electricity is there or not is checking the bulb. The bulb is not glowing. So the bulb doesn't glow as long as the field flux is constant. But the moment I move the magnet, notice what is happening. The bulb is glowing. Why? Because the flux through the coil is changing. So that is what Faraday's experiment found. When you change something, you move something, there is electricity which is generated. Even if you keep it inside, no matter how strong, no matter how many turns, doesn't matter. If the flux is constant, there is no electricity. So I can change the number of turns. I can change the loop area. You will see right now there is only single turn, and you will notice there is a very small magnet. So barely any electricity is being generated if I move it, because area is less, turns are less, magnet is also very small. So magnetic field is also very small. I'll increase the magnetic field. I will increase the number of turns. I will increase the area, and now see, there is more electricity which is being generated because there is more or larger change of flux happening in the same time. Is that clear? In fact, we can make a SHM problem also out of it. Look at this, there is this magnet and there is a coil and there is this What do you say? Bulb. So I can just visualize how the magnetic field is piercing through this coil, right? Some lines are piercing through it, so there is a flux passing. Right now there is constant flux, so no electricity. But let me move this magnet either like this or like this. You will notice there is change of flux. So that change of flux is what is causing electricity to be generated. So if I attach a spring mass system and leave it, oh wow, we have now got a generator. You take a spring mass system and leave it, so it will keep on oscillating and it is now generating electricity. Isn't it amazing, guys? But I have a simple question for all of you. Can I take such a spring mass system, keep it inside a coil and just leave it? This bulb will keep on glowing forever. I can just relax. I don't need any power at my home because I have now created a generator. So I just need to buy a spring from the market and take a mass and just pull that spring mass system and leave it, and I can just relax because this will forever generate electricity for me. But obviously something doesn't feel right, because if that would happen, then we all would have such spring mass systems at home and we will never ever pay our electricity bills. There is some catch in this. Can you identify what is the catch? Why this will not happen forever? This will happen only for a small time. Yeah, what is the reason for it? Can you guys quickly think and tell me, guys? Yep. Can you guys quickly think and tell me? What is the thing which is preventing this from happening forever and forever? Yeah, what is it? Something is there. What is that something? Can you figure it out? Imagine electricity is being generated continuously. Where is that electrical energy coming from? It is coming from the mechanical energy of the spring mass system. So it can't come from magic. You cannot generate electricity from magic. I know it doesn't feel like it is touching it. So you are wondering, sir, it is wirelessly transferring. Yes, bro, it is wireless. Most of the forces are wireless. Earth is pulling the moon via wireless force only. It is not contact. So here also, it's a non-contact kind of force. So you will notice that electricity is being generated, electrical energy is being created. So from somewhere it should get that energy, and that somewhere is the mechanical energy of the spring mass system. So ideally what will happen is this spring mass system will slowly stop oscillating, and once all the energy from the spring mass is delivered, that's it, it's done, it will stop and no more electricity will be generated. That's the end of story. So energy has to be conserved. Okay, it cannot violate the energy principle. Anyways, so these were the questions that we discussed, and this is one of the most important discussion which we had, where you change the angle. So now let us solve some more questions, guys, coming up on your screen, and here it is. Here is the first question. The magnetic flux linked with a coil is given by phi t square plus 3t plus 16. What is the magnitude of the EMF at 4 seconds? Luckily for us, flux only is given, so we don't have to do much of calculations to find the EMF. EMF is d phi by dt. So all you need to do is take the derivative of the flux, which is 5t square plus 3t plus 16. So 5, as it is, derivative of t square is 2 times of t. This will be 3 into 1. 16's derivative, which is a constant, will be 0. So this will become basically 10 times of t plus 3. That is your EMF. The real question is at 4 seconds. So EMF at 4 seconds, substitute time as 4 and then get the answer. 10 4s are 40 plus 3, which is 43. So 43 volts will be the answer, my dear. Okay. So t square 2, so 10t, and this was 3t, so 3, that's it. So at 4 seconds was asked, so 10 into 4, 40, 40 plus 3, which is nothing but 43 volts. Yeah, just differentiate this. Perfect. Let's move to the next question. Yeah, answer is B. We just got it. Okay. Let's move to the next question coming up on your screen. Here it is. A coil of some area having some turns is making 15 revolutions in a magnetic field, what is the peak of the induced EMF? The word peak of the induced EMF means when you take a coil and rotate it, the EMF is something like this. This is your peak, meaning the amplitude. So the amplitude we all know is magnetic field area omega into n, Born, BA omega n. I just gave you this formula right over here. Born is the peak of that EMF, maximum EMF, BA omega n. So everything is given, I believe. So we just have to substitute it. Magnetic field is 0.04. Area is given to be 400 centimeter square. So 10 raised to negative 4 in meter square. But omega is given in revolutions per second. Do not worry about it. 15 revolutions means 15 into 2 pi radians, which are being covered every second. So omega will be 15 multiplied by 2 pi radians per second. Lastly, number of turns, how much is it? 20. That's it. That will give me the answer. Okay. So that was nothing but 20. Solve this and see if you are getting the answer as close to 3. You should get close to 3. So 3 volts approximately should be the answer. 3 volts approximately should be the answer for the amplitude. Okay, don't get confused. This is, I have written A, but that is not area. This is amplitude. Amplitude. So the amplitude of the voltage or the EMF, amplitude of that EMF is BA omega, which comes out to be close to 3 volts. Perfect. Okay. Let's move to the next question on your screen, and here it is. What does it say? There is a coil resistance which is placed. It is rotated by 180 degrees in 0.25 seconds. What's the average EMF which is created? Okay, let's visualize. We have a coil. Some radius, some turns, and it is placed perpendicular to a magnetic field of something. Perpendicular means the area vector will be here and your magnetic field will be here. So you can see the coil is definitely perpendicular to the magnetic field. So the area vector will be in the same line. That means theta will be 0. Theta will be 0 degrees. Now you are rotating that coil. So when you rotate that coil by 180 degrees, what will happen? Even the area vector will turn. So the area vector will now point this way. Area vector will now point this way. So yes, your theta will be 180 degrees. Magnetic field is still going to be this way only. Magnetic field is still going to be this way. So it is definitely 180 degrees. So you have rotated it by 180 degrees. So there is changes in flux. So question is, how much is the change in, how much is the average EMF being produced? So we know the average induced EMF will be how much ever is the change in the total flux divided by the time. So flux change means magnetic field into area into cos, or I will just do one thing. I will just write it as final flux minus initial flux divided by the time interval. Now if you ask me what is the final flux, I will say it is B into A into cos of 180 degrees. But there are, I think, n number of turns, so I will put n over here. Initial flux B into A into cos 0 multiplied by n again. The whole thing divided by the time. Notice how cos 180 is actually minus 1. Cos 0 was anyways 1. So this is negative BAN. This is also minus BN. Minus BN will become minus 2 BAN. So minus 2 BAN, the whole thing divided by the time interval. Now it's just a matter of substitution, nothing else. And we are only interested in the magnitude of it. So the mod sign will come, negative sign will not even matter. So magnetic field, how much is it? It is 3 multiplied by 10 to the power negative 5 Tesla. area, we can write it as pi multiplied by radius square, which is 0.1 square. Number of turns is nothing but 500, and the whole thing divided by the time. How much is it? 0.25 seconds. So that is 0.25. Because we are only interested in the magnitude of it, so ignore that negative sign. Solve this and you shall get the answer as 3.8 10 to the power minus 3. Approximately 3.8 into 10 to the power minus 3 volts. Is that okay? The catch is many people forget cos 180 minus 1. This is also cos 0, which is 1. So negative and negative will add up together to become 2 times. Some people end up cancelling it. Bn minus Bn. Do not forget that area vector has turned by 180. So final flux is not Bn. It is negative Bn. It's like the change in momentum problem. A mass comes, hits and rebounds and goes. Change of momentum is not 0. It is mv minus mv. So Bn was there before. After that it is becoming negative Bn. So the change is double 2 Bn magnitude wise. Is this clear concept? Okay. Why did I substitute EMF as A? I didn't really want to do that with the same symbol. This was amplitude. So amplitude symbol is A. So I just wanted to mention the word amplitude. I didn't want you to confuse between amplitude and this A symbol of area. So that's why I changed it later. I wrote amplitude as E. Okay. So just compare it with this over here. The amplitude is BA omega n. I hope now it is clear. Okay. Because otherwise you will get confused, sir. Are you writing area 2 times over here? This is not area, man. This is area. Here this is amplitude. Okay. Fair enough. Now is it clear? Great. Now let us see another question. This is similar to that. So I feel you can take this up as homework. Instead of 180 degrees, the question says 90 degrees. So try to solve this as homework and put the answer in the comment section. Put the answer in the comment section. Alright, later on. Cool. Now let us go to the next part, which is Lenz's law. Lenz's law gives me the direction in which the current will be created or the voltages will be flowing created in that coil. Because Faraday's law gave me only the magnitude, mod of it. It never told me which side is higher voltage, which side is lower. That is what Lenz's law will tell me. So Lenz's law gives the direction of induced EMF by energy conservation. By energy conservation principle. It's based only on that. Energy conservation principle. So 2 keywords to remember. Lenz's law gives me direction and it is based on energy conservation. How does it give? Here is the thing. Imagine you have a coil. Imagine you have a coil, and in that I notice that this particular flux passing through it is becoming stronger. Just take a situation where this first situation where the flux has become stronger. Flux has become stronger. Second situation where it has become weaker. If the flux has become stronger, means there are more number of magnetic field lines within this territory. So there are more number of field lines within this territory. Weaker means the number of field lines have reduced. That's what it means. So stronger flux, weaker flux. How Lenz's law works is, if the flux becomes stronger by any way, either by changing area or by changing angle or by changing the magnetic field, doesn't matter. Somehow it is becoming stronger, the flux, or it is becoming more. Then try to oppose that change. Always oppose the change. It's become stronger, right? Make it weak. How? You're going to oppose it. So to oppose, what you will do? You will create a magnetic field towards yourself. This is the direction of the induced magnetic field. If the flux becomes weaker, then help it. Oh, you are becoming weak? Don't worry, I will support you. So you support it in the same direction, obviously. So you create an induced magnetic field in the same direction. Now use your right hand rule. That's it. You are going to get the answer. In order to create this induced field, if you hold your thumb of the right hand in that same direction, your fingers will curl. That curled fingers represent how your current is traveling. That was your right hand rule. If a current is going in a coil, the curled fingers gives me the direction of the current. The thumb gives me which direction the magnetic field is generated. So here the current will be generated like this. So this is the direction of induced current. Here the magnetic field is induced inside. So put your thumb inside. The fingers go like that. So it is clockwise in this scenario. So this is the direction of induced current. So the idea is that the current induced will always create an induced field to oppose the change of magnetic flux. To oppose the change of magnetic flux. That is your Lenz's law. So the current will always be in such a direction that it will oppose the change of magnetic flux. If it tries to increase, then it will try to make it weaker. If it tries to decrease, it will try to make it stronger. It's like a support system, also opposing system at the same time. I am very good, Deeps. I hope you are doing great. Hi, Prinsu. I hope you guys are understanding, enjoying in detail, guys. That's very, very important. Is this clear, everyone? Pakka? Very nice. Very nice. So let's take some examples to really understand this. Say for example, I tell you that listen, there is a coil over here. Let me show the axis of the coil so you guys are very clear about it. This is the axis. So you can visualize this in 3 dimensions. Okay. Now we take a magnet. Let's say we take a magnet from here. And let's say this is North Pole, this is South Pole. Then we'll put it here first so that we get more space. Here like this. This is North Pole, this is South Pole. Here, this is, let's say here like this. This is South Pole, this is North Pole. Now I'm going to move this magnet and I'm going to see which way is the current going to be generated. That's all. Okay, that is my whole agenda, guys. So first time I'm going to take this magnet, I'm going to try to move it here. If I move this magnet here, there will be change in flux, there will be induced current in it. Same way I'm going to take this magnet and I'm going to move it this way. Then I'm going to move it the other way. That's all. That is the whole agenda of this particular problem. First, quickly think and tell me, if I move this magnet inside this loop, then at that moment, where will the current be induced? Just think about it and answer in the chat box. Now I know there is a complex way of doing it. Complex way is just going blindly by the rules, seeing whether the flux is increasing or decreasing. So you will notice the moment I move this magnet here from the North Pole, there will be magnetic field lines which will be coming out of it. Obviously, there will be magnetic field lines which will be coming out of it like this. Correct. So when I notice this particular magnet going towards it, the flux is increasing. Because the flux is increasing, to to oppose that increase, I will have to create an induced field in the exact opposite direction. So my induced field will be like this. So if induced field is like this, hold your thumb, fingers give me the direction of the current. So current will obviously be like this. So this is the direction of induced current. Great. Very good. Now look at this particular scenario. South pole always takes in the magnetic field lines. So magnetic field lines are coming like this, right? So these are the magnetic field lines going inside that bar magnet. Now when you move away, what happens is lesser and lesser flux travels right side. Notice when this magnet was here, most of these lines were going within that loop. When you move it away, you will notice fewer, and because this line will now come over here, lesser number of lines flux will pass through that coil. So if the flux reduces, it's weakening, I have to strengthen it. So you will notice the magnetic field induced will be in the same direction. It will be in the same direction. So if the magnetic field is induced in the same direction, curl your fingers. Thumb is in the direction of the field. Curl your fingers, it is coming like this. So induced current is this way. This is the direction of induced current. Is that clear? This is one way of looking at it. But I will teach you a shortcut. So do one thing, go back and think what is exactly happening. By energy conservation principle, flux change is always opposed. Whatever is happening, you have to oppose it, right? Okay. So the job of this coil is to somehow oppose the motion of the magnet. So why not look at it like this? I have a magnet trying to move towards me, which I don't like, always have to oppose. So me being a loop, to oppose it, I will have to repel it, isn't it? I will have to repel this magnet. Which is trying to come towards me. How do I repel? By making this an electromagnet and making sure the north pole faces the north pole and this is the south pole. So north facing north will repel that particular magnet. So the north pole of the coil is here. So if this is north, this is south, hold your thumb from south to north, which is how the magnetic field will go from this electromagnet. Naturally, the induced current will be in this direction. Does that make things much simpler now? Isn't it much simpler, guys? Think about it. I know it has to repel because it is trying to come close. So what I will do, I'll create a north pole here from this coil. So now it is going to stop it. It is going to lower its speed. So north pole here means curled fingers go that way. So that is the direction of current. It's much easier. Same way you can do it over here. This bar magnet is trying to run away and I really don't like it. Why are you running away? I am going to oppose it. So if you're running away, I am going to attract you. So it's always opposite. I'm going to attract you. In order to attract, what do I need to do? Think about it. This particular coil, what do I need to do? Think about it. I will need to make sure that to attract it, south is attracted by north and obviously this side will be south. North and south will attract. So hold your thumb from south to north and automatically you will see your fingers going like this, meaning the current will be in this direction, which is exactly what this is saying. So this is a much easier way by attraction and repulsion than going by the traditional way. Oh, the flux is increasing, also it will oppose, so this will be the direction, so then I will hold my thumb, then I will get my curled fingers. It's a much longer way. So you are cutting out few steps. So if I use the same technique over here, let's say whether you can guess it, very quickly within few seconds only you can give me the answer. So this will work for any kind of question, guys, by the way. So if it is moving like this, I do not like it going away. I will be like, why are you going away? Come towards me. So I will start attracting this coil, a magnet. So if I have to attract, that means the north has to be facing the south. This side will be north. So if this is south, this is north, curl your fingers. So this is the direction of current. Very easy. Within few seconds you can get it. Same way over here. It's coming towards me. I will be like, what the hell? Why are you coming towards me? Go away. So I will say repel. And when I say repel, south has to face south. And this will be the north side. This is south, this is north. Move your thumb like this. Fingers curl that way. So this is the direction of current. Got it? So that's how easily you can get, using Lenz's law, the direction of current. Cool? So always try to oppose the change, and in specific scenarios, if that is not working or not clicking, go by the basic rule. If it is becoming stronger, weaken it. If it is becoming weaker, strengthen it. So the poor needs to be given money, the rich need to be taxed so that you take away money. So that's what Lenz's law is. It's more like a communist law, you can say. Alright, it's trying to be the Robin Hood, robbing from the poor, robbing from the rich and giving it to the poor. Here it was becoming weaker, so it's making it stronger. This was becoming stronger, so it's making it weaker. So it's basically a Robin Hood communist kind of a law. Okay, easy, right? So easy. Perfect. So let's move now to some questions. I think you can easily answer this. There is a bar magnet which is dropped completely through a vertical copper tube, and the acceleration of the magnet is asked. Which of the following is true? A is equal to G, A is less than G, A is more than G, and A is equal to 0 throughout. So what has happened is, you have taken a tube like this and you have dropped some kind of a magnet inside of it. Now we expect the magnet to fall inside this tube with an acceleration of G, but that won't happen. What is the reason why when it drops down inside this tube, you will see the acceleration is something different. In fact, the answer is it is less than G as long as it is inside the tube. What is the reason for it? Yep. The reason for that, why is the acceleration lesser than G? Because the moment it enters inside, Lenz's law will come, it will oppose, man. This is like a coil. When it tries to move in, the motion is inside. What will this copper tube, coil, etc. do? It will say, bro, why are you coming close to me? Go away, man. So it will try to repel it. So to repel it, it will create an induced current, and maybe the induced current will go like this. So this is how the induced current will be in this case. So I'm assuming something. And because of that, the force will be lesser than what you would expect. So the acceleration is also naturally lesser. In fact, there are beautiful videos on YouTube. You can search for it on YouTube. Dropping. This is 16 seconds video. It's a brilliant video. Let's see whether it plays. Yes, hopefully it plays. See, this person is taking a copper tube and he's dropping something, and you can see slowly it is coming down. Can you see that? It's exactly the same problem, guys. Very, 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 very slowly. Isn't it amazing? Yeah. So just watch that video. It's very interesting because electricity is being created in that copper tube because flux is changing. So it will oppose that change by Lenz's law. Anyways, one more thing which I wanted to also tell you is that many books, after learning Lenz's law, what they do is they write this induced EMF like that. Instead of just putting d phi by dt, they say it is minus d phi by dt, but it is okay, it is understood, man. This negative sign is because of Lenz law, and this d phi by dt, basically this Lenz's law gives me direction, nothing else. Minus tells it is opposing, and this is what Faraday gave me, and Faraday only gives me the magnitude aspect of it. The magnitude aspect of it. Okay, so this is what most of the books will write with a negative sign, but most of the times we are not interested in that negative sign. That is okay, just like F is equal to negative kx. When have you used negative so religiously, apart from some derivation, right? You just use the magnitude of it. Great. So let's see the next question on your screen, and here it is. Aluminum ring B faces an electromagnet A. The current through A can be altered. Okay. Which statement is correct regarding their interaction? If current is increased, the electromagnet will attract the ring. If current is decreased, it will repel. If current is increased, A will repel. When I is increased or decreased, A will attract. Now, I'll tell you, for such type of questions, see, play logically. You cannot sit and check all the options, right? Use some brain, use some logic, common sense. There are two options with the same, experiment, like current is increased, but the outcome is different. So 100% one of them usually will be the answer. Think of it like that. Current is increased, then A will attract or A will repel. And I know either it will attract or repel. So think like this, that when I am increasing, either it will be attracting or it will be repelling. One of them must be happening. It can't be like I have increased the current and it is neither attracting nor repelling. Because when I increase the current in that electromagnet, flux will increase or change, and definitely there will be some attraction or repulsion. Oh, so 100% B option won't be correct, D option won't be correct. Eliminate it. Did you understand the logic? Did you understand the logic, my dear? Why we are eliminating B and D? I'm not telling about this question. Many times this will happen. Force is increasing, then displacement will increase. Force is increasing, then displacement will decrease. So whichever two options is creating that confusion will be the correct answer. Other options, Chumma they have given. Make sense? Right. Okay. So what will happen? Just try to figure out what will happen if current increases and we have an electromagnet. So we have an electromagnet. Okay. And if I have an electromagnet, and what is happening is this current is increasing. If current is increasing, what will it do? It will obviously increase its magnetic field. So magnetic field will also increase 100%, and it is facing a ring. A ring is here. This is our ring. Okay. This ring I am calling it as B. This electromagnet is basically A. Do not get confused between this B and this B. This is your field, guys, that's all. This is your field which is increasing. So flux is increasing. So if flux is increasing, what will happen? It will not like that increase in the flux. It will not like that increase in that flux. So it will try to oppose it. So if it tries to oppose it, it will have to create a magnetic field this way. It will have to create a magnetic field this way. This will be the induced field direction. If this is the induced field direction, hold your thumb, your current will go like this. Basically, this is how the current will go. But that's okay. What will I do with the current? That's of no use. Just think like this. This coil will always oppose 100%, right? It will 100% oppose because you are increasing the current. So it will oppose by decreasing the flux. So this coil, the orange one, will have north here, south here, whereas this yellow coil, because it was generating the field that way, that north will be here, this south will be here. That north will be here, this south will be here. Notice how north and north are too close to each other. So what will they do? They will end up repelling. So 100% they should repel. That is the answer, option C. So don't even have to actually find the direction. Think like this: when I increase the current, the flux will increase, so it will oppose. So this coil will oppose. That's why its north will be this side, but this coil was creating the flux this way, so the north was anyways here. So both the norths together, 100% will end up repelling. That's all. Okay, is that clear? Yes, Tanmay, what's the doubt, man? Let me know in the chat box. Let's do the next question. There is a loop, resistance, and moving in a uniform magnetic field. constant in time and space, exists perpendicular to the loop. The induced current in the loop is okay. So we have this kind of magnetic field, which is, let's say, going inside. You can take it outside also. It's there everywhere. It's there uniformly. It's existing in space, and it is constant also with time. Okay, that's what it means. It's not changing. Uniform field. You are taking some kind of a conducting square loop. This is your conducting square loop, and it is moving inside this coil. Field. So there is motion. Question is, what is the current inside of it? A lot of people are going to start calculating, but I will not calculate. I'll tell you why. See, when this square will move to a new place, let's say over here also, notice how whatever flux was there here is also there over here. If this is the flux passing through this coil, here also the flux is the same, because B is same, area is same, angle is same. So the flux has never changed. The flux passing through that has never changed. So flux is constant. So EMF has to be 0. Hence the answer will be D, guys. There will be no current, there will be no EMF. That's it, because same flux is passing through it. Okay. I'm glad, Vaishnavi, you're watching me over here. Okay, thank you. All right. So that was your Lenz's law. Now, this brings me to the concept of, while moving this rectangle or square, there was no electricity being generated. What if I just move a part of that wire without having a complete connection? Instead of a complete loop, let's say it was just a rod. Then will voltage be generated? Will current be generated? That is my thought process. So the concept of motional EMF comes into play. Now, what happens is, this concept of motional EMF is taught in different ways to many people. So I will teach you both the ways. And sometimes people don't teach anything like that. They just go with the formulas. I will not do that. I will tell you two ways of looking at motional EMF. Imagine I have taken a rod and I'm just moving this rod like this inside a magnetic field. I'm just moving this rod in magnetic field, and I'm trying to work out whether some kind of electricity will be created in this rod, because it's in motion in that magnetic field. So, just vaguely thinking. So what I do is, I imagine it to slide on some rails. These are conducting rails like this, on which this rod is sliding. So let me mark it over here. These are your conducting rails. This is your conducting rod. So because it is in motion, what happens is, look at how much flux is passing in this particular region. Look at how much flux is passing in this particular region. This is a proper circuit, closed loop. So because it moves, after some time, this rod might come over here after some time. So I'll just say after some time, it has moved slightly. So notice how there is some extra flux which is created. Notice how there is some extra flux which is now created in that extra region which is there. Can you notice there is some extra flux which is now created over here? Yes, everyone, there is 100% some extra flux which is created over here. and this extra flux means magnetic flux is changing, and if there is change of magnetic flux, delta phi is existing, 100% there is EMF which is induced, EMF which is induced in this particular circuit. So yes, a moving rod creates electricity. Moving rods induces EMF. One way of looking at it is by taking a conducting rail and try to move it on the conducting rail, immediately you will start seeing electricity being produced. But the problem with this approach is that students or anybody will argue, sir, what if only the rod was moving? What if the conducting rails were not there only? Then how do I visualize it? Because then I do not see a loop over here. Then what is the guarantee that the loop is like this only? Why can't I take the loop like this, right? Why is it only rectangular? Why can't I take it something else shaped? So all those sorts of weird ideas start to pop up in your head. So that is why I do not appreciate this method so much, although it gives me a fair idea that if I had a conducting rails like arrangement and I moved the rod over those conducting rails, I see a conducting path and 100% there will be electricity, current, etc. flowing in that path because flux is changing. So via Faraday's law, we can definitely see, there will be electricity created. But still, I am not convinced because I had to bring in that loop over there. What if it was independent? What if it was independent? So right now we have used Faraday's law. So what we have used is basically Faraday's law. Let's say I did not know what is Faraday's law at all. Can I still get it? The answer is yes, and that's what I want you to see. This is crazy, guys. This is the approach of H.C. Verma. That's why I suggest use H.C. Verma book for understanding theory. I recently made a video. I don't know whether you have seen this video. We saw it on the channel. Where is our channel, man? On the channel only I had made this video. You know, how many of you have seen this? Where are the JEE advanced questions taken from? And many of the questions were from H.C. Verma, apart from the other books which I have talked about in that video. With proof, I have given screenshots of those books, similar questions, and many times it has repeated or rather been inspired also from H.C. Verma. Anyways, H.C. Verma is a very important book conceptually if you want to understand it, because NCERT is very confusing. It's good for boards, but please don't depend on NCERT for JEE, at least when your targets are more than 95 percentile. Okay, because when you try to go to good percentiles, you are trying to target JEE Advanced, you are trying to target BITSAT, you are trying to target IIT, NEST, UGEE kind of examinations. So obviously you have to go to H.C. Verma, man. Okay, so that's where you will see that concepts become stronger. So I am taking a rod, and let's say this particular conducting rod, this is my conducting rod, and this conducting rod is in motion, and it is in motion inside a magnetic field. There is no area to worry about, there is no flux, there is nothing, there is some magnetic field. There is some magnetic field in which it is moving. Now you will start wondering, I can't explain, I can't use Lenz's law, Faraday's law, nothing, whatever I have learned. I have to go back to my basics. So, fair enough, I'll go back to my basics. I will focus now on the material of the conducting rod. So this is my material of that conducting rod. If there was no magnetic field, all those atoms which are there inside that conductor, whether it is copper, aluminum, God knows, they will be electrically neutral. Their nuclei will have some positive charges like this, positive charges like this, and there will be a small electron cloud covering those positive charges. It's become too dark. Small electron cloud covering those charges, something like this. See if you are able to visualize. So nucleus positive, electron cloud negative, that red one. And they are electrically neutral, they are balancing out each other, they are perfectly centered. There is no shift, so net charge is zero basically. Everywhere, field, everything is zero. There is nothing abnormal which is happening. Now, this is when there is no external field. When there is no external field, meaning magnetic field outside is zero. But observe what happens the moment it is in motion. Observe what happens the moment that conducting rod which is there, it is in motion. The moment it is in motion, these charges will start to experience force. Q, V cross B. And we have studied this in magnetic field effects. Q, V cross B. But the problem is a nucleus, even though it experiences force, can't move. It's rigidly making up the structure of that solid. If a nucleus moves, the atom moves. That's where the most of the mass of the atom is concentrated, and it will drag other electrons along with it. So that is not what we are looking at. So forget the positive charges for now, because that is rigidly fixed for that conductor or any such solid. So focus on the electron. So negative charge moving that way, which way will the force be? So a negative charge in motion like this, in a magnetic field which is, let's say, going inside, which way will the force be? Q, V cross B goes up, but it is a negative charge, so it comes down. So the force on that negative charge is going to come down. Oh, crazy, sir. So you mean to say these negative charges will start to come down? Exactly. In fact, those electron clouds will also drift, or at least those negative charges which are free to move will start moving. So you will notice something like this. You will start noticing something like this. Those electron clouds will begin to, I would say, distort themselves like this. Positive here, positive here, positive here, positive here, positive here. Yeah, the negative charges, can you see they are going down like that? So there is a separation of charges. So you will see essentially, if I write it down properly, the negative charge is now accumulated over here, and this side has become positive. I mean, I'm saying this side is more negative and this side is more positive. That is a better way of looking at it. Because of which, there is now going to be an electric field which is created, because this side is now at a higher potential, my dear, and this side where the electron cloud has now migrated, so that will be at a lower potential. That will be at a lower potential. So there is a potential difference. And what does a potential difference do? It also creates electric field. Oh wow, crazy guys. So there is going to be an electric field which will go from obviously the positive charge to the negative charge. Is that right? So there will be an electric field which is created. There will be an electric field which is now created. Perfect. So that electric field is now created because of you just moving those charges. That conductor. Sir, won't all the electrons eventually come down and accumulate and settle down over here because that's where the force is? Absolutely right question, and that's what H.C. Verma also says, that will not happen. Why? Is because this electric field which it own created now will begin to oppose the motion of these charges coming down. Think about it. You move the conductor inside the magnetic field pushes these electrons down. Charges get separated, electric field begins to form. Now the next batch of those electrons which are now getting motivation that okay, let me go down because magnetic field is pushing me down, that will be opposed by this electric field. Because of the negative charge, the force will be upwards. So this force will be due to magnetic field, but at the same time the electric field which is there, that will then create a force upwards, due to electric field. That's it. It will create a force upwards and it will create a kind of an equilibrium, and once that equilibrium is reached, these electrons will feel like there is no motivation to go down. They are balanced because magnetic force is pulling them down, but at the same time electric field's force is pushing them up. So no more electrons get accumulated over here, and it will now be in steady state. So there will be, yes, higher density of electrons here, higher density of positive charges here, a potential difference being created, and a balanced steady state which is now being preserved as this conductor begins to move. Is this understood? Everybody with me on this? If these forces are balanced, if you tell me these forces are balanced, I can in fact now say that due to the electric field, the force will be QE, and due to the magnetic field, the force will be QVB. This looks like something what we have done before. So you will get E is equal to VB. E is equal to basically speed into magnetic field. Now this electric field is nothing but how much ever potential difference we get, divided by the length of the rod. This is nothing but how much ever potential difference we get, delta V. So this is capital V actually. This is voltage difference, potential difference. So Q has got cancelled. E is delta V divided by the length of the rod. Therefore, my potential difference will be length multiplied by the speed. This is the speed, guys. By the speed multiplied by the magnetic field. So a potential difference is created. So this delta V stands for the potential difference between the ends, of that particular rod which is now created. It is L into V into B. So now once we know there is a potential difference which is created, great. If you now think of taking this rod and connecting it to any such circuit anywhere over here, this is a wire, immediately you will see this is now a closed circuit where that rod now behaves like a battery, which is then connected to this wire which is there. This battery has that voltage difference of L into V into B. Is that right? This battery has a voltage of L into V into B. This voltage of that equivalent battery which is created by the moving rod in that magnetic field is called motional EMF. Understood this concept? It's quite deep if you think about it. One thing leads to the another. So no need of Biot-Savart's law, anything. So we'll repeat this entire concept so that it will replace, you simulate this, visualize this and close your eyes if you want later on. You move this rod has equal positive negative charges centered, producing no electric fields. Everything is at rest. You move this inside the magnetic field. The magnetic field will apply a force on electrons. Positive charges stay as it is, they are nucleus. The magnetic field using QVB force pulls it down. So the electrons start to accumulate down. but a simultaneous electric field prevents further electrons from going down, because that electric field will push it upwards and an equilibrium sorts is achieved. Once that equilibrium sorts is achieved, we can equate the forces due to electric field and the magnetic field, and we see the electric field being voltage difference per unit length. We get the voltage difference for the rod is length of the rod speed into the magnetic field. If I take such a rod and I connect it to the wire, then I will say that this rod behaves like a battery whose voltage is LVB, and that voltage is what I call as the motional EMF. Clear? Very good concept this is. Now you should also realize that if I did not use this wire, if I just leave it as it is, there will be EMF, but there will be no current. This thing, get it inside your head. There is a battery, it is not connected to anything. So there is EMF, there is voltage, but there is no current, because where will the current go? There has to be a complete circuit, right? So if there is nothing connected here, that's it, there is no current. The moment you connect this wire, that's when the current comes. So yes, this particular current comes, the current is produced only if the circuit is complete. Only if the circuit is complete. Else it's only the EMF which is generated. So this LVB is basically called the motional EMF. This is called the motional EMF, LVB. Okay, so this is the motional EMF. A moving rod produces voltage across its ends when it moves inside a magnetic field. That is called motional EMF. Great. But sir, what if the rod is not moving perpendicular? Sir, what if it is at an angle? What if the velocity is making an angle? So then, if you take the worst of the worst scenarios, you take multiple cases and then you start seeing some trends and you make a formula. So the formula comes out to be like this. You take any rod, no matter how you place it, doesn't matter. This is my L. You take L as a vector, doesn't matter. You assume it in any direction. Let's say you make that rod move in some random direction, doesn't matter. This is velocity. And let's say there is some magnetic field, I don't know, it could be in some other direction also. For now I'm putting it like this. Then the EMF induced, this entire thing is just like I said, a battery. Is just like a battery. This is called as the motional EMF. Due to motion, how much EMF is generated? That motional EMF E is given by L vector dot producted with V cross B. V cross B. That is what the EMF is. It is a scalar triple product. It is a scalar because when you do the dot product, the outcome is a scalar. There are three numbers here. That is why it is called triple. So that's why it is a scalar triple product. If by chance this was not a dot, this was a cross, this would be a vector triple product because the final outcome would be a vector quantity. There are three numbers, so triple, outcome is a scalar, so scalar triple product. You have learned this or will learn this in mathematics, scalar triple product. So remember this formula, guys. In the worst of the worst scenario, you might have to use this. This formula is not given in NCERT, by the way. Okay, so you need to know this for JEE Advanced. Because JEE Advanced question, you might get an angle and you might have to use this. I have given the notes, man, of the previous chapters. It should be there in the app. Yeah, it should be there. Okay. Hi Jia, hi Santosh. I hope Lac cross G8236, this concept was clear. Yes, Sunil, it's clear. Okay, great. Utkarsh, I'm from Laksh batch. Can I watch my lectures to cover my backlog? It is more than enough, man. Actually, I'm teaching JEE stuff more than NEET. So, it will be more than enough. I can guarantee you, you will get 180 out of 180 in NEET if you watch my classes. I mean, for JEE, though, you will get. Even for NEET, I can tell you. And I'm not telling this chumma sake, okay, you watch my classes. It's okay, you don't watch my classes, that's also fine. There are 100 more teachers you can watch. They will also produce the same rank, not an issue. But if you are watching, you are having faith, please continue and watch it. And I can guarantee you that, because I remember a lot of times I get these messages, like how I get these messages some time back. I in fact happened to meet that student also in an interview. And he said that he was watching my YouTube classes. He was a NEET student from a town and he was a dropper, and he got 176 marks, basically left one question, that's all, and that too because it was a bonus question and he was confused whether the answer will be correct or wrong. Otherwise he would have got 180 just through YouTube classes. Just imagine. Okay, so it is possible. Chemistry was messed up for him, so chemistry got very less, so he messed up his rank a little bit, but physics 176 out of 180 is a huge deal, man. Yeah, it looks like a tomato. What looks like a tomato, man? Yeah. Oh, if it is not uploaded, I will just mention the admin to upload it. Don't worry. Okay. Oh, this one looks like a tomato. Oh yeah, these looks like tomatoes for some reason. Yeah, you're right. When I was drawing it, it didn't look. It's very close for me. But from here, it does look like tomatoes. Amazing. Great. L dot V cross B. So you're going to tell me in all these scenarios whether EMF will be generated or not generated. Okay, I'm going to draw some scenarios for all of you, like this, like this, like this, like this, then like this. The rod is over here. Okay, these are all the rods, and I'm going to show how it is moving in every scenario. The first case, it is going like this. In next case, it is going like this. Next case, it is going like this. Next case, it is going like this. You have to predict how will the EMF be, or if it is there, okay. If it is not there, you have to tell me that also. Then it is moving like this. Then it is moving like this. Magnetic field is also very important. Okay, this is magnetic field in the first case. This is magnetic field in the second case. This is magnetic field in the third case. This is magnetic field in the fourth scenario. This is magnetic field in the fifth scenario. Then this is magnetic field in the last scenario. All these scenarios, where will the EMF be, if at all, if it is there? Use this principle, this formula. It will be needed. What you need to do is first do V cross B. Then once you do that, do the dot product with L. L can be assumed. Please remember, assume the direction of L. Always assume L, because sir, how do I take for a rod? L is this way or this way, because both ways you can get it. So it's okay, assume. Assume and see what is the answer. If by chance E comes out to be positive, that means whatever you have assumed is correct. Whatever you have assumed for that length. So let's say length was assumed like this, it is correct. So the battery that will be placed will be exactly like this. If by chance, let's say the EMF comes out to be negative, that means whatever you have assumed is wrong. So actually the battery would be like this. That's what it would mean. So whatever you assume is correct means EMF is exactly the same way. If it is negative, it's opposite to whatever you have assumed. That's all. So just go by that logic and you will get the answer, guys, one by one. First, do L dot V cross B. V is there, magnetic field is inside. So V cross B is over here. For everything, I'm going to do V cross B first. velocity is up, magnetic field is towards me, V cross B guys, V cross B is this way. Okay, so V cross B I'm going to do first every place. Here velocity is up, magnetic field is also towards me, so again right side, so V cross B is over here. Okay, here V is in left side, magnetic field is inside, left cross inside will go like this, so V cross B will go like that. So this is the direction of V cross B. Okay, then over here V cross B will come towards me, V cross B will come towards me. Here V is up, magnetic field is inside, so V cross B is going like this, left side. Yep, V cross B, V cross B, yeah, it is going left side. Perfect. First part done, taken care. Yeah. All right, then. All right. Santosh, what stupid questions? Santosh, don't waste our time here, right? If you're not serious, please go to some other channel, ask these stupid kind of questions, right? And anything that you want to ask, please don't ask me over here, right? Don't waste my time, don't waste others' time. It's a very serious channel because we are focused purely on JEE, man, right? I am a JEE teacher. JEE, I need to make sure that you guys crack IIT. So if you want to crack some stupid faltu statements, please go somewhere else. Don't waste my time. Yeah. Okay. Now moving on, over here V cross B is done. Now let's take the dot product with the length. Dot product with the length. So where is that length? Length is here. Oh, length is like this, guys. No matter how I take it, like this or like that, the dot product will be a 0, right? Whether I take length here or I take here, angle is 90. So two perpendicular vectors, dot product is 0. So EMF is big fat 0. V cross B is here. My length vector is here. Oh, I can again see it is perpendicular. That's it. The answer for the EMF will be again 0. Got it? Similarly, over here, you will notice if I take length vector in the direction of V cross B, the answer will be positive because both vectors in the same direction, dot product comes out to be positive. Cos 0 is 1. So 100% EMF is there and the EMF will be like this. The EMF will be like this. So EMF is definitely there. Okay. Now, next scenario, V cross B is here. If I take length exactly in the same direction, V cross B dot product with the length will be positive. So yes, there is an EMF and that EMF will be like this. So EMF is there even in this scenario. How about this? Okay, length vector is towards you in the direction of V cross B. Imagine length vector is towards you in direction of V cross B. So their dot product will be again existing because cos 0 is 1. So cos 0 being 1, EMF is there. So EMF is there towards you. So EMF is there towards you. Last question, V cross B is here. Length vector will be towards you. So that is perpendicular. So perpendicular means dot product will be 0. So EMF will be 0 in this case. So that's how you get whether EMF is there or not there. Clear? Everyone about this? Absolutely, ma'am. Yeah. Pakka. Okay. Simple. Using this scalar triple product. Now there is one unique type of problem which you get where you might have a rod, but it is not it is not translating, it is rotating. This unique kind of question. This is length L. And it is now being rotated inside a magnetic field. It is now being rotated. Okay, it is now being rotated inside a magnetic field, something like this. This magnetic field is B. I feel there will be EMF induced inside this rotating rod. There is a standard formula which comes after derivation, but it's a very laddu derivation. It's not that difficult. How do I figure out how much EMF will be generated? See that L dot V cross B can be used when the rod is translating. But when it is rotating, then you need to be very careful. So what you do is, you take any segment of that rod, and that small segment is a small length which is translating in that magnetic field. So for that small segment, we know how much EMF will be generated. So if I take small segments throughout the rod, each small segment will act like a small battery. Adding all these batteries together, I will get the net combined battery, which is the net motional EMF. So the logic for this particular question is, we take up a very small segment of that rod, and when we focus on that small segment, you will notice, because it is in motion, it will behave like a small battery. L is up, so V is upwards, let's say V cross B here. So yeah, most likely EMF will be like this. So there will be a very small EMF which will be generated. So for that entire rod, you can think as if many such small EMFs are there till the last end over here, and all of them are basically in series. So when I add all their EMFs together, I will get their total motional EMF for the entire rod. So this is the total EMF for the entire rod. So that is the thought process for this problem. Are you able to visualize this? Now, how much is that small EMF? We can get it. It's not that difficult. So if my small element is somewhere over here, this element will have a length of dx. It will have some velocity v, and that dx will be at a distance of x from the center. This velocity will be omega into radius being x, it will be omega x. So that small EMF will be dE, which is length into v into b. Length is dx, speed is v, magnetic field is b. So it will become dx into omega x into b, which can be better written down as b omega x dx. B omega x dx. So for the entire rod, so I can mention, for the entire rod, the total EMF will be integration of all these Chintu-Mintu EMFs. So integration of this Chintu-Mintu EMFs, which is B omega x dx. Out of that, B and omega is constant, so bring it outside. So I only will have to technically integrate x with dx. Limits of the integration: the first element will be here, last element will be here. So x will start from 0, and when x becomes the length, you will stop it. So 0 to L basically. So therefore, the EMF will be B omega L square divided by 2. So this formula, you better remember it. Direct questions come. B omega L square by 2. Alright. Thank you, Peaky Blender. Means a lot, man. Yeah. So that is the answer for a rotating rod. Example will be, you are riding a bicycle. Just visualize this. It's a crazy thing. You are riding a bicycle. Alright. This is the road. A bicycle has many metallic spokes within it. Metallic spokes are there, right? You would have seen. It could be even the car. In olden times, they used to have spokes, but now they don't have. They have alloy wheels, which are still metals. Anyways, these are spokes. Now, Earth also has its own magnetic field. So, imagine a region where there is Earth's magnetic field like this. Imagine Earth's magnetic field. This is Earth's magnetic field. Earth's magnetic field, which is like this. And because this wheel is rotating, you will notice each of these rods inside this wheel will behave like a battery, So you will start seeing small, all of these rods behaving like batteries like this, batteries like this, batteries like this, Chuma, I have shown few of them only. And now all these batteries are having a common point and the other ends are on the rim of the wheel. So 100% there will be an EMF which will be generated between the center and the rim of that cycle. Okay, any tire which is made of metal basically with spokes. So you will see there will be a voltage difference which will be created inside that metallic element between the rim and the center. But usually these voltages are negligible and very small for you to detect. But yes, they are existing. Okay. Instead of a rod, you can have even a conducting element also. Yes, definitely. So let me go back and make it very, very clear. Actually, good you raised this point. Okay. So over here, forget this rod. Imagine I have any random shaped body. Forget a rod. Just forget this. I have some randomly shaped body. And that random body is moving in a random direction in a random magnetic field. Doesn't matter how much. Okay. Now, if you take any 2 points inside that conductor, any 2 points, and mark their distance as L, then those 2 points will have a potential difference. So there will be a potential difference, or I will say there will be EMF between those 2 points which I have marked, and that will be, my dear, L dot V cross B. So that's how it works. Okay, you can take any 2 points inside that conductor. It need not be the ends of a rod. It works for any shape. Is that clear, Shailesh? Yeah. Such kind of tricks, such kind of traps might be led by JEE Advanced, might be led by IIT, might be led by UGEE. Okay. So that's where you can expect these kind of things, because usually you think of rods by what if a solid sphere comes. Oh, don't worry. It will still work, man. You just need to assume 2 points and the distance as L. It will still work. Okay, great. Let's solve some questions coming up on your screen. These are simple standard questions only. A rectangular loop with some length L is situated in a uniform field. Connected resistance is 2 ohms. Two parallel resistances of 6 ohms and 3 ohms are connected across the rails. Okay. All right. The force required to keep the connector moving with some speed. A rectangular loop with a sliding connector is 1 meter. Resistance is also given. Two parallel resistances of 6 ohm and 3 ohm are connected across the rails. Okay. And the force required to keep them moving. So let's visualize this diagram first. You have this sliding connector. Then you have these rails like this. These are your rails. So this is having a length of 1 meter. It is moving with a speed of 2 meters per second. There is a resistance over here which is 2 ohms. Two parallel resistances of 6 ohms are connected across the rails. This is 6 ohms and this is basically 3 ohms. Okay, are connected across the rails. The force required to keep the connector moving. Now the moment you move this, what will happen? This entire rod will behave like a battery, man. This entire rod will behave like a battery, which will be LVB. But there is a resistance here. So that resistance of that rod will behave like an internal resistance. And this remaining rails have some resistances, one over here and one over here. basically they will behave like external resistances. So convert that into first a easier, simpler circuit. So then it's easier to solve the problem. So we have to figure out what? I think current. All right. No, sorry, force. So for the force, we will need current, by the way. See, in order to keep it moving, right? Why do we need a force? You need to understand that first. Because there will be a ILB force exactly opposite. ILB force exactly opposite because of the current which is flowing. So because of the current which will flow in the circuit, because of the EMF, that current will experience a magnetic field force of ILB. So to counter that, we will need an extra force so that it continues to move. So that is the first thing that we need to visualize only in this problem. Why we need force? Why can't I just leave it? Why can't it keep moving? Oh, because there is motional EMF. Oh, that is why there is current. And the moment there is current, magnetic field will apply force and it will try to stop it. So that's why we need to continue its motion by an equal and opposite force. So this is what I will say. External force is equal to IL into B. Current is equal to the total voltage, which is EMF, divided by the total resistance, and this into L into B. So what is that EMF? EMF is LVB. So L into V into B divided by R, and this L into B. So this will become L square B square into velocity by the total resistance. So length, we all saw it is 1 meter, square of it. Magnetic field 2 Tesla, square of it. Velocity 2 meters per second. So just keep it. Resistance 3, 6 and 2. So 6 plus 3 plus 2, guys. So 2 square 4. 4 into 2 is 8. Perfect. Is that right? And this 6 and 3 will make it 9. 9 plus 2 is basically 11. So 8 by 11 Newton. Unless the diagram is something else, I mean, this should be the answer. So I'm guessing the diagram was not clearly mentioned. So, you know, I don't know, maybe parallel meant something else over here. So I'm not really bothered about these options. So I'm just saying two resistances of 6 and 3 ohms are connected across the rails. So it makes the problem look simpler. Otherwise, we need to be given what the exact diagram is. So L square B square V divided by resistance. Is that clear, everyone? Yeah? Great. Perfect, Shailesh. Sir, is seeing important subtopics for 2027 help me score this much range? First of all, John, I would ask you, is 500 to 550 even enough? No, right? So why are you even targeting that? Number one. Number two, don't you have enough time right now? 1 year is, I know it's not exactly 1 year, but still you have decent amount of time till next attempt. And next year, they are saying NEET will have 2 attempts or whatever, multiple phases and all of that. So when you have so much time, when you have multiple attempts, I don't see any reason why you should do only important subtopics, number one. Number two, I don't see that point of scoring 500 because still government medical college you will not get. So please target 650 plus. Please do not leave anything when you have 1 year, especially when you are taking a drop. You have all the time because you don't have school, you don't have college, you don't have worry of boards. So that is your goal. So target higher, man. Don't target lower. If some teacher is telling you how only do important topics, they have not produced results. So you cannot produce results by skipping things. I just happened to meet today only some of the students who are learning in offline, and some of them are JEE, some of them are NEET students. They are sitting in the center or in the library or in the study area. They are droppers I'm talking about, and they're sitting for 10 hours apart from the coaching. I'm saying apart from coaching, 10 hours. You give them a homework, they are not only solving the homework, they are doing more than it. You tell them about the textbook modules, they have solved it. You ask them about their backlogs, they ask me what is the meaning of backlogs, because they say no sir, there is nothing like backlogs. We have done whatever the teacher has taught. If the teacher has taught me something today, I have completed it. So this is the level of the students, and this was just maybe a small group of students whom I saw. And imagine how many such centers will be there, or how many such students will be there across a city, so many states, so many places across our country. So that's where the competition is. So we cannot afford to lose marks because we did not study only. The potential only will reduce. So complete literally everything. Got it? Yeah. If you're a partial dropper, then yes, you will have to compromise, and if you're looking for dental, yes, then you can think of it, man. Next question. How do we solve it? A conducting rod rotates perpendicular bisector, uniform parallel magnetic field, the potential difference across the end. Very similar question we just solved. You take a rod and you rotate it. How much is the EMF which is generated? Magnetic field is there. Come on, very laddu question. Come on, everybody spam the answer in the chat box. Everybody spam. A lot of people are going to say half B omega L square. Then you will realize, oh, wait a minute. It is rotating about the center, not the edge. Yes, sir, right. So actually speaking, this is your battery. This much. And the length is exactly half. So it is half B omega L by 2 square, which will make it half B omega L square by 4, which will make it B omega L square by 8. Then a lot of kids are going to mark option D. But that is also not the right answer. Because read the question. Between the ends they have asked, not between the center and the end. So this battery will be facing this way. Now, if you ask me, what's the voltage between these 2 points? It's obviously 0. Why, sir? Because if this is 0, this will be plus E. If this is 0, this will be also plus E. So if you ask me what is the voltage difference between these 2 points, obviously both are at the same potential. So the answer will be 0 volts. Hence, B is the right answer. Is that clear? So a lot of kids misread the question. Okay, many mistakes are possible. Is that clear, everyone? Why will a CBSE student even watch this video, man? Because this is higher level, more than CBSE, not from board's perspective. I'm going very deep, more than NCERT this is. So if you want concepts, yes, you can watch it. But other than that, I feel it will be slightly beyond what is expected for CBSE. Slightly, in fact, quite a lot. A wheel with some things is rotated. What is the EMF? So this is your homework question, my dear. This is your homework question. Use half B omega L square formula. You know omega from here, converted into radians per second. You know the length. You know the magnetic field. But there is a catch. It's in Gauss. I have explained you what is a Gauss. It is 10 raised to negative 4 Tesla. It's a different unit basically of magnetic field. 10 raised to negative 4 Tesla. So you know B, you know omega, it's just a matter of conversion. You know length. So just use the formula, you will get the answer. Alright, answer I have kept it on the next slide. Now let's go to eddy currents concept. Let's go to eddy currents concept. What is this? It's very simple. If you take any conductor, and let's say you are moving a magnet around it. Let's say you are taking a magnet somehow and moving around it. The moment you move this magnet is in motion. This magnet will be creating its magnetic field, which might be passing through that conductor. And this field will be changing within that conductor. So the magnetic flux flux which is there, which is passing through this conductor, will change. Because the magnetic flux will change, what will happen? By Faraday's law, there will be induced electricity. So this electricity, where will it go, you might ask? Because sir, you have not connected any circuit across it. You're right, I have not connected any circuit. So it will make its own circuit within the conductor. It's a decently sized chunk of conductor. So what it does is that it makes its own circuit within that conductor. It does not look for an outside path, it looks for an inside path, and you will see that it will follow the path of least resistance, and maybe you will see currents going like this. Maybe you will see some current going here like this, like this, like this. Maybe over here you will see some other current going like this. So these are called the eddy current loops. These are called as the eddy current loops, which are formed within the conductor. They are not looking for a conducting path outside, but inside the conductor itself. So I am saying that any moving magnet, or whenever there is relative motion between our conductor and the magnet, it could be electromagnet also, then there is change of magnetic flux, then there is change of magnetic flux. Because of the change of magnetic flux, there is EMF which is induced by Faraday's law. Because there is EMF which is induced, there are currents within the conductor, and these currents within the conductor, they are called as eddy currents. And because the conductor will have some resistance and there is current, I squared R losses will happen. I squared R loss will happen. And what is this I squared R loss? Which is basically heat loss. That means there is energy which is lost. Energy which is basically lost. So the mechanical energy is lost. The motion which is happening, it has mechanical energy. So the mechanical energy is lost. So these eddy currents always cause loss of mechanical energy, and that loss converts itself into heat. The best example of this is an induction kind of a stove or an induction cooker. What happens is it uses these eddy currents principle only. There is an electromagnetic coil, and that electromagnetic coil is very close to a metallic plate. What happens if you change the current's direction? The magnetic field will change direction. That will cause changes in the flux. When the flux changes, electricity is produced in that metallic conductor. When that electricity currents are produced, there is heat which is being created. That heat is exactly what is used to heat whatever is there on the stove or that pan. The same concept is also used in high-speed railway braking. When your train is at a very high speed, if you think friction will stop it, well, that's right, but the friction will cause so much wear and tear that you might have to replace the brake pads very frequently. And for such a huge train, the momentums and energies are so huge that you cannot have or afford such brake pads. So what they use is electromagnetic braking, where your train wheels are anyways metallic in nature. When you want to reduce the speed of the train, electromagnets come very close to those wheels, or those electromagnets get activated. When a magnet and a wheel has a relative motion, it produces eddy currents. Immediately these eddy currents will cause heat loss. So if heat energy is created, by law of conservation of energy, somewhere in the universe, some other form has to be gone, and that is the energy of the train. So the kinetic energy of the train will convert itself into heat. Yes, there is lot of heating which will happen, but I'm okay, I can deal with heat. I will let it go. There will be a very hot break, that's okay. But I am definitely not encountering any wear and tear as such. So this is what high speed rail braking looks like using eddy currents. Is that clear? RC circuit will you cover? I have already covered. So if you go back over here, RC, current, electricity. In this part only I have done RC circuits. Oh, sorry, not here, not current, electricity, my bad. In capacitors. Where is capacitor? Where is capacitor, man? Here. This lecture. In the end, I have covered RC circuits, both charging, discharging, time constant, decay, how the exponential graphs will look like, everything I have covered. Okay, so you can watch this. Okay. All right. Thank you, Giga. You are finding this amazing. And usually students watch it as recorded because some students prefer me talking in 2x and 3x. They message me saying, sir, we watch you in 2x and we cannot afford so much of time. And then you can ask me, sir, why don't you teach very fast? Because I have to think of everybody. If I talk so fast, then half of the students will start watching me in slow motion, 0.5x. So either ways, you will have some bunch of students watching it either fast or slow. So I prefer teaching at an average pace, not slow. So that if you want, you can watch it fast. Great. So let's talk about some questions now. First question on your screen, here it is. An eddy current is produced when a DC current passes through the wire, a bulk piece of metal is subjected to varying magnetic flux, metallic wire is moved in a magnetic field, steady magnetic field is applied across an insulator. Come on. Yeah, for 11th also I know you guys have a lot of backlogs. Don't worry about it. I will make a plan. And by the way, you can always use different tools, like there is this tool called Cap Compass, which I have been talking about on Telegram and even on Insta, everywhere. So that tool can easily plan your schedule. No matter how many backlogs you have, you can set your goal, everything, and it will plan accordingly. So use these tools, guys. It's there. The link is there on Telegram and even Instagram. So you can check that tool out and you will see. It will plan your day, it will plan your months till your target exam. No matter what exam you are preparing for, whether it is JEE mains or JEE advanced, BitSat, everything. That's the best tool you can use. Okay, capcompass.app. If you type, you will get it. So the answer for this, yep, it is B, a bulk piece of metal in a magnetic flux. When you vary magnetic flux, EMF by Faraday's law, EMF means current, current means loss of heat will be generated, meaning eddy currents are created. That's it, that's the answer. Moving on to the next. If you have a pendulum which is oscillating between the poles of an electromagnet, there are poles of an electromagnet in which this is oscillating. The pendulum stops quickly. Why is it that the pendulum is stopping after some time? What is the reason behind it? Think, when that metallic pendulum is vibrating, it is having relative motion with the magnet. When there is relative motion, that's it, change in flux means EMF, means current, means eddy loss. So eddy heat losses are happening. So that's what is the right answer. So electromagnetic damping from eddy currents. Damping means reducing something. You are making it smaller. You are damping it. You are making it less. That's the meaning of damping. It should work, Peaky Blinder. I mean, it's not broken or anything. It should work. Or if it is still not working, then I will have a look into it. But it should work. Okay. Yeah. Just check it out on Telegram, because or you can just enter that code. If you want, I will put that code also later on, so that you know, you will be able to take it very easily. All right, no issues. We'll fix it. Now there is one more interesting question on these eddy currents and motional EMF, which usually comes at look something like this, where you have these rails, you have this rod, this has some resistance, this is also some resistance, there is some magnetic field B like this. So when you try to move this rod with some speed, what happens? There will be motional EMF in it, and that motional EMF will create a current inside it. So V is there, B is inside, so V cross B is up, so motional EMF will be upwards. So this rod will behave like a battery, VLB, like this, connected to this external resistance via this small internal resistance over here. So definitely there will be current in the circuit, and once there is current, what happens is there will be some energy loss which will be created. Can we figure out how much that energy loss is per unit time? So a question can come, what is the external power which is needed? What is the external power which is needed to maintain the speed? So the logic goes something like this. Whatever power I will need from external force will be completely going into heat energy per unit time. Why? Because I'm not changing the momentum of it. So whatever x joules of work I will be doing in pulling the rod, that x joules will be converting itself into heat, because there is no other energy which is being stored, nor is the momentum or kinetic energy of the rod changing. So the external power will be going as power loss in that circuit. And power loss, we all know, will be I squared multiplied by the resistance. But the resistance will be the total resistance of the circuit, isn't it? So we have to take the total resistance, which is R plus R. You can also do V square by R, that's also the same thing. Current is nothing but EMF divided by the total resistance, so it will be R plus R. So square it, guys, into basically R plus R. So it will just become E square divided by R plus R. How much is EMF? The EMF is LVB, so it will be L square V square B square divided by R plus R. That is the answer. That much power will be needed in order to sustain its momentum and energy. Else what will happen if you do not give that energy? The power loss will take over, and you will see that the rod will slowly eventually stop, because the energy is being lost in the circuit. Okay, is that clear, everyone? So this kind of questions are also very popular. Now let's go to one more concept, and after that we will take a break before going to inductors, because that will completely switch our thing. So this concept says that whenever you have a magnetic field which is changing, then it produces induced electric field. Very, very important. Changing magnetic field, changing the magnetic field induces electricity, or basically electric field, induces electric field. And the formula for that comes from here. Faraday's law says that minus d phi by dt is your EMF. So if I imagine a loop, which may not be actually a loop also, it might just be my imagination, it's just a path. Imagine this is just a path. This is a closed path. This is a closed path. Let's say I start from here, I go like this, I go like this, and I come back over here. So it's a closed path. Every time I'm moving, I'm traveling some distance, let's say dl distance. I'm traveling dl distance and I'm coming back to the same point. Now, EMF means voltage, and if you remember, voltage is nothing but integral of field with the displacement. Try and recollect. Field is dV by dr. So voltage difference is E times of dr with a negative sign. Yeah, I hope you remember this. So magnitude wise, if I try and solve this particular equation, forgetting the negative sign, you will notice this EMF is nothing but the potential difference in a loop. If you start from here and you come back here, that is what that EMF of that loop means, which is induced. So it is potential difference within that loop, and that potential difference has a formula, integration of electric field dot displacement. Here displacement is dl. But since I'm coming back to the same point, that's why I'm forced to use cyclic integral, because it is a closed path. On the right hand side, it is the rate of change of flux, but we all know what flux is. Flux is nothing but magnetic field dot area vector. Magnetic field dot area vector. So this formula is then called as Maxwell's equation. It's one of the Maxwell's equation. The other three we'll see in EM waves if needed. But for now, this is the formula which you can call it as the one of the Maxwell's equation. It's one of those equations in this form. This E which you are seeing, right? This is the electric field which is now being created because my magnetic flux is changing. So you will notice that there is an electric field which is now being created because in this region, that flux was changing. So that flux was changing. So maybe these were the magnetic field lines. This magnetic field was changing, which created change in flux, which created EMF, which means there is a voltage difference, which means there is electric field into the length, which you have to consider. So this is the formula if you want to find out how much is this electric field. If you want to find out how much is this electric field. This electric field is called as the induced electric field. So changing magnetic field induces electric field. And you can notice in this region, the magnetic field has changed. Either it has increased or decreased, something has happened, but it has changed. Is this clear? So from Faraday's law only I have got this. There is nothing very different. It's just that yes, it looks very scary because on one side you are having a dot product who is derivated. On the other side, you have a dot product which is integrated, that too in a cyclic closed integral form. It just looks scary, but when you try to solve it, it is not that scary. Trust me. Okay? Alright. I'm so glad astronomy, you loved it. And astronomy says that it's working. So Peaky Blinder, I think it is working, man. So maybe you will have to just try it once more. Okay? Or manually. I will help you with the manual code later. Induced electric field due to... Now, one peculiar thing about these induced electric fields, which is very, very important. You might be wondering, sir, where are they starting from? Where is the charge? That is the most common question. But let me tell you, it is not starting from anything. It is not ending from anything. Rather, it is just a closed path. So these induced electric fields, this is very, very important. These induced electric fields these electric fields which are induced, they are always closed paths. And yes, these induced fields are created because my magnetic field was changing. dB by dt was not zero. Notice how there is no charge anywhere. There is no free charge which is creating it. There is no free charge which is creating it. But compare that with our regular electric fields which used to come from charges. It used to go like this. It used to go like this. Remember? Your regular electric fields. It used to always start from a positive charge and end at a negative charge. These are your free charges. There is a start and there is an end. They are not closed paths. They have a clear start. They start from some point and they will definitely end. So that is significantly different. For the first time, you are seeing electric fields being closed paths like magnetic field. So this tells me that this is a very different kind of electric field. The nature of this electric field is only very different. It has come not because of free charges, rather it has come because of changing magnetic field. There are no charges only in there. So this electric field which is induced is always closed loops or closed paths, unlike start and end with free charges. Now another big difference is that because we have studied in electrostatics, whenever you have electric fields in this manner, you move anyhow, it doesn't matter. Let's say I'll take a path. Let's say you start from a point and you come back to the same point. If you do the total work done calculation, on a charge which is being moved, you will see it is always zero. That means it is conservative in nature. It is a conservative field no matter how you move it. Is that right? We have seen this. But here, even if you take a simple path like this, every time the work done will be positive because field will apply a force in the same direction. So positive work, positive work, positive work, positive work, positive work, positive work, positive work. Whole time positive work. So the total work done will not be zero. So you can take any path, doesn't matter. As long as you are coming back, you will see if you are taking this charge, the total work done in a closed path will not be zero. That means it is non-conservative field. It is a non-conservative field. Very, very important. So induced electric fields due to changing magnetic fields are not conservative in nature. They do not come from free charges. Their paths, field lines are itself closed. But the fields which come from your regular positive negative charges, they have a definite start and an end. And they will have conservative nature. Is that okay? So this is a very important distinction between these two kinds of fields. Okay? All right. Right. Notes of the past chapters, definitely I will tell the admin unique soul. I'm about to write JEE advanced pattern exam. I could solve some Erodo problems myself and also model questions, but I keep getting stuck with some time consumption. Is there any way? No, astronomy, you have to deal with that time. In fact, that time is the most important time. Even if you are taking some time, it is the time where you are building your brain. So you are opening up your brain. Erodo problems are not easy. Some problems might take hours. It's perfectly fine. Okay, but make sure when you are spending the time, it is actually used for your brain thinking. Because see, when you are thinking and you are taking, let's say, 1 hour to solve a problem. Chumma, I'm saying an example. And then you finally get to something, then you're looking at some solution, then you get something, then you waste some time or you're thinking something, then maybe after 2 or 3 hours you get the answer. The process of thinking has actually wired your brain. It has made that logic very clear, because next time you get such a question, right, you will be able to do it in much faster time. But that will not happen second time. You will take 3 or 4 efforts of similar problems. That's when that habit will come. So let that habit come. Don't think that is a waste of time, but you are actually reducing your actual effort during the exam hall. So use it properly and think properly, or don't just randomly keep doing overthinking during that process, because usually people overthink. Oh, why am I not getting? You feel stressed. Don't take that stress. Use it for building your brain's logic. That's all. Okay. So coming back, if you take a loop, you will notice there will be electricity created because there is magnetic field which is changing. Whenever there is electricity, that means there is EMF. If there is EMF, meaning there is voltage difference. Where is this voltage difference? In the loop. Meaning, if I start from one point and come back, I am seeing there is a voltage which is being created in that loop. Now, compare this with your regular Kirchhoff's voltage law, where we had studied, you start from a point, you go across any circuit and come back, the total voltage sum will be 0. That is what is funny. Kirchhoff's law of voltage is no longer valid. You are coming back to the same point and you are saying there is a voltage which has been created. That is why I am saying that this electric field is non-conservative in nature. When you come back to the same point, there is a voltage difference, and voltage is field multiplied by distance, because field is voltage by distance. So field multiplied by distance is the voltage, but in integral form it will look like this. Since we are coming back to the same point, I have used cyclic integral. That is the only reason. My start and my end is same. So I started and ended at the same point. So that is why this closed integral has come. d phi by dt means the rate of change of flux. Then I said these electric field lines do not have a start or an end. So if you take a charge, let's say here, you will see the field will keep on doing positive work, example. So when you come back to the same point, total work will no longer be 0. Means it is non-conservative. Just you need one path to prove, one path is enough to prove the field is non-conservative. Any path. Okay. But if you can't find any such path, then the field is conservative in nature. Is this clear? Alright. Perfect. Amazing. Amazing. Very good, man. Very good. Crocodile, I am everywhere, man. What to say? I hope this is clear. Yeah. Man, I can't do such comparisons, man. Sorry. Now, let us do this particular question. This is a very important question. A uniform magnetic field exists in a cylindrical region and it changes at certain rate. The magnitude of the field at a distance r less than r, we can also do r more than r, by the way. Okay. So, this is a very important derivation. You have to better remember this formula. That will be easy. There is a cylindrical region of R where the magnetic field is there. Okay, this is my cylindrical region, and in this cylindrical region, my magnetic field is existing something like this everywhere. Okay, that magnetic field is changing at a certain rate, and that rate I am calling it as alpha. Okay, next I am saying at some distance r from the center, let's say I will call this as small r. Later on, we will say this is our later on what we'll do, we'll extend this and we'll say this is our r, and at this point we will try to find our electric field. For now, let's stay inside And we know electric field lines will be circular in nature or closed loops basically. So one such electric field line I have shown here. This is my electric field. This electric field is circular in nature. I am interested how much is this electric field. Next time I will go outside that cylindrical region where the magnetic field is there. So the electric field line will be in a bigger circle like this. So I am interested how much is this electric field. So two scenarios, inside versus outside. First let's go inside. Okay, so as per our new Maxwell's equation which I have just mentioned, E dot dl is rate of change of flux. So what you do is, instead of writing it in that complex form, think of it in a simple form. Cyclic integral field dot dl, cyclic integral field dot dl is just rate of change of flux. I am traveling this path, notice. So the length that I am moving, dl, the length that I am moving, dl, 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 and coming back at the same point is that pink path. So dl is along that pink path. Electric field is also along that pink line which I have drawn, circle which I have drawn. So the cyclic integral is also on that. So when I travel that path and complete a loop, in that loop there is some flux. So let's imagine that flux. That flux will be basically this one over here. Can you visualize this flux within that loop? Can you now think how much is that flux, guys? Can you visualize how much is that particular flux which I have shaded? Yeah, how much is that flux which I have shaded? Think about it. Radius is r, area will be pi r square, magnetic field is B, so it will be B multiplied by area, which is B multiplied by pi r square, small r square. Is that right? Okay. So if I substitute it over here, it will be derivative of B pi r square. But B is not constant. Pi and r square are constants. So I will get dV by dt. But wait a minute. I know what is dV by dt. It is nothing but alpha. My RHS gets sorted perfectly. Now let's move to LHS. Okay, is RHS very clear? Okay, so flux within this region. Why this region? Why not this region? You have to consider this path which I have traveled, dl, dl, dl. Within that path, what is the flux? Okay. Now, integration of E dot dl, the dot product will be with angle 0 because electric field and length are in the same direction. So it will be E dl cos 0 degree. The field at the same distance will be same. So E is a constant magnitude. So E comes outside and I just have cyclic integral dl. Now what is cyclic integral dl? Think about it. dl, 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 dl being added, it is the perimeter of that pink curve, which is the circle, which means it is 2 pi r. Very good. Now you can see pi goes, this r also goes. So I am left with only the electric field magnitude, which comes out as r times of alpha divided by 2. R alpha divided by 2. That is the answer. So if you don't like alpha, you can also think of E is equal to R divided by 2 into dB by dt. Now this formula, you better remember it, guys. R by 2 into dB by dt. That same answer will be there over here. R alpha divided by 2. Yeah, see, R alpha divided by 2, option B. That is when you are inside. Okay, when you are outside, the only thing which will change in this entire expression will be, see, this is still cyclic integral E vector dot dl on the left hand side. E is like this, you are going around it. Let's say you start from here. You start moving small distances with dl, dl, dl. Every time you will see E vector and dl vector are in the same direction. So angle is 0, cos 0 is 1, E is constant. So on the left hand side, you will still get the same thing only. not much of difference. So cyclic integral dl will be total perimeter of the circle, which is still going to be 2 pi r. dl being added across the perimeter is 2 pi r. The difference happens on the right hand side, where you have d phi by dt. The change is now the flux is not there in this part. Yeah, this part, this annular region does not have magnetic flux. Field is only trapped inside. So technically speaking, this is my region of magnetic flux. This shaded region which I am drawing is the region of my magnetic flux. So my magnetic flux will be same irrespective of what my R is. Visualize. Even if my pink circle expands, flux is still there only here. No matter how big it becomes, the flux is only there here. So flux only is dependent in that small region, whatever it is there. So my flux will be only the field in this region multiplied by the area of this region, which is pi, into the radius, whatever that radius was. I think that radius is given to be capital R. Now you are outside of it. So I will say my flux is field multiplied by pi r square, and it is a constant. So when I take the derivative of b pi r square will come outside, dv by dt will stay as it is. So it will become pi r square multiplied by alpha. Okay. Now in this situation, notice pi gets cancelled, but r will not get cancelled. There are two different r's. Don't make that mistake of cancelling it. So it will now become r square divided by 2 small r into alpha, meaning it is E is equal to r square by 2r multiplied by dv by dt, if you prefer writing it in that form. So both inside and outside, now you know the electric field. Notice how when you are outside, the electric field is inversely proportional to R, and notice how when you are inside, the electric field is directly proportional to R. Just like how used to happen in our sphere shell problems, there are different proportionalities inside and outside. Same logic being applied here. You will notice the electric field is differently proportional. Inside it is proportional to R, outside it is inversely related to R. Okay, so that's the logic behind it. Is this clear? How to find the electric field due to changing magnetic fields? Due to changing magnetic fields. So that was the answer. All right. So now it's time for inductors and inductance, but for that we will have to refresh our minds. So we'll take a small break. Okay, we'll take a 20 minutes break or something, and we will return. Okay, we will return after the break. Cool. Right. See you guys in a bit. I'm audible and visible to all of you. Just let me know quickly in the chat box. Yes, the break is over. Yeah, so sorry guys, little bit more time we took, but it's okay. We had to anyways refresh. You guys had to have your dinner. Yeah, if you are watching it recorded, anyways, you will be forwarding it. Shall we begin with the next concept? Everybody, let me know if I'm audible and visible. Quick check, voice check, health check, video check, everyone. Okay, great. So let's begin with the class. And yeah, great. So let's start. Now we are going to start with the topic of inductors and inductance, and it's related to whatever we have been studying now, which is Faraday's and Lenz's law, which comes under EMI. Now what is this inductor? Let me tell you. See, it's a new component of your electrical circuit, like you had wires, switches, resistors, capacitors. This is the next electrical component, which is called inductor. And an inductor has inductance. Just like a resistor resists the current passing through it, a capacitor stores the current in the form of charge and energy, electrical energy in it. You will see an inductor also resists changes in current. You might find it similar to that of resistance in the beginning. Later on, you will realize that actually it's very different from resistance. See, I'll tell you an example. You are passing some current, let's say 2 amperes in a wire. The 2 amperes is passing, a resistor will try to reduce that current. But an inductor will not do anything to it. Because if the 2 amperes is 2 amperes from the last couple of minutes and seconds, inductor says, oh, the current is not changing, I will not do anything. But the moment the current begins to change, either increase or decrease, doesn't matter, but any kind of change, the 2 ampere becomes 2.1 amperes or 2.2 amperes or 3 amperes. Immediately inductor will say, wait, why are you changing? You are 2 amperes, no, why are you changing? Don't change. That's what inductor does. It will try to oppose any kind of change. Now, when it opposes, it's not like it stops it completely. So, a 2 ampere current trying to go to 3 ampere will not increase suddenly because there is an inductor. So, that inductor prevents sudden changes or fluctuations of current, and you will see instead of raising the current suddenly, the current grows onto 3 amperes slowly, and eventually it will reach, let's say, 3 amperes. After it reaches 3 amperes, it's a steady, smooth current. Inductor will be inactive. It will say, okay, you are 3 amperes, you are staying 3 amperes, I am sitting quiet. Resistance will still do its job of opposing. But if the 3 amperes now tries to change to, let's say, 4 amperes, or even tries to come back to 2 amperes, again inductor will say, wait a minute, why are you changing? Don't change. I will resist the change. So it will not allow the current to drop immediately. Okay, so that is what it is. Yes, RC circuit is completed, man. Music, we had done RC circuits long time back. So make sure you see that in the capacitors. Okay, all right. Okay, great. All right. Amazing, amazing. So here is how I will draw it graphically. RC circuits, please check capacitors. Okay. This is my current. If I do not have any kind of inductor in the circuit, you will see the current changes are sudden. So if there is a current like this, suddenly it will increase. suddenly it will increase, and suddenly it can even decrease also. And again, if you try to change the current or even reverse the current, that's also okay. Suddenly it will change. All of this is without an inductor, only just resistance. But the moment inductor comes, you will notice here it will be as it is, there will be no change. But the moment you try to change, it will slowly take its own sweet time before it reaches a steady value. The moment you again try to change, again it takes some time, sweet time, to reduce, and it reaches a steady value. Again it stays constant, and again when you change, again it will take some time before it reaches a new steady value. So this is with an inductor. So inductor resists the change. So inductance is a property of inductor, is a property of an inductor. Inductor is that device, and such a device has a symbol of this, like a coil, like a solenoid. This is the electrical symbol, guys. So you should know this electrical symbol of an inductor. So whenever you have an inductor, this is with a symbol, like resistor is like this, capacitor is like this, battery is like this. So same way, inductor symbol is round curled things like a coil. Then you will see that property is it resists changes in the current. It resists changes in the current, and that's why it is sometimes also called as electrical inertia. In electricity, it has inertial property, so it is called electrical inertia. Inertia is a tendency of any body to resist some change. So electrical inertia is that property which resists the change of current electricity. That's why electrical inertia. You will see a lot of times the formulas in mechanics and electromagnetism are similar, and you will see wherever in mechanics the term mass or moment of inertia comes, in electromagnetism that will get replaced by inductance. That's what you will generally see. Okay? Awesome, awesome. Perfect. Now, how do I find out inductance? How do I define that inductance? There are two types of inductances that we can have. One is self-inductance, other is a mutual inductance. There is a small difference between both of them. Both of them are based on Faraday's and Lenz's law. But who is it changing or who is it trying to resist? That's what categorizes or differentiates self versus mutual. Say for example, there is a wire and it tries to change its current. Then the resistance will apply on itself. It will try to resist any kind of change on itself. That is called self-inductance. There is a wire beside you and the current in that wire beside you is changing. You try to resist that change in that another wire. That is mutual inductance. It's like saying you are in a classroom and teacher is teaching and you get distracted. You change your orientation, you look outside the window. Then you realize, oh no, I have to study, I have to get 99 percentile, I have to get IIT Bombay, I have to get IIT Chennai. So you are bringing yourself back, you are controlling, you are in control. That is self-inductance. Your friend starts looking outside. Your friend starts looking outside, you hit him on his head and like, hey, look over there. Why are you looking outside? That is mutual inductance. Okay. So that's what happens. Anyways, let's begin with the actual formal definition of self-inductance first, because that's what is the major part. Mutual is a very small part. So if you take an inductor, this is our inductor, and you pass some current I through it, that current will create its own magnetic field within that coil, will create its own magnetic field within that coil. So I'm showing those magnetic field lines, although we might not show it all the time. This is my magnetic field. This magnetic field will create magnetic flux on each of these coils. Will create magnetic flux because it will pierce through each of these coils every single time. So it will create a magnetic flux throughout that inductor. So that flux will depend obviously on the field, and that field will indirectly depend on the current. So I can then say that the total magnetic flux, throughout that inductor is directly proportional to how much ever current is being passed through that inductor. Because if I change the current, the field changes. The field changing will change the field lines, which will indirectly change how many lines pierce through those coils, which means the flux changes. So the magnetic flux is dependent on the current, and I do not like proportionality. I always need a constant in mathematics. So I will replace that proportionality with a symbol L. That L is basically inductance. So L stands for the inductance of that inductor. Inductance, which is the electrical inertial property of that inductor. How much does it resist the change? If the inductance is large, it will take more time to change. So if the inductance is small, it will change quickly. That means it does not resist so much. But if the inductance is large, it will take more time to change. So small inductance will allow changes very easily, but a large inductance will resist any kind of change which are happening in the current. Okay. How much is the unit of this particular inductance, guys? So it's very easy to see how to define the unit of this inductance. If this is magnetic flux, which is measured in Weber, right? It is measured in Weber. The current is measured in ampere. Then this new unit of inductance is Henry, is basically Henry. So a Henry of inductance is when you have a Weber of flux which is produced per ampere of current. So this is how you define the unit aspect of the inductance. A Weber of flux, you pass a ampere of current and a Weber of flux is created. That is a Henry of inductance. Okay, simple and sweet. Now, when you take an inductor and change the current through it. When you take an inductor, I will write it as L. This is the current. And let's say the current changes, the flux will change. Flux changes, electricity, EMF is generated. So you can find out how much is the EMF which is generated in this if current changes. If this current changes. If this particular current changes, there will be an EMF which will be generated, and that EMF, simply put, if you use Lenz's law, which has a negative sign, with Faraday's law, which has a negative sign, and this is Faraday's law. This flux happened to be how much, guys? We just calculated it. It was L times of I. So it will be L times of I. Usually L is a constant. So L goes outside. So I will have L times di by dt with a negative sign. The negative sign is just symbolic to say, listen, if your current increases, I will try to reduce it. If your current reduces, I will try to increase it. That's just a symbolic way. Magnitude wise, it is L times di by dt. Magnitude wise, it is L times di by dt. Okay, so this formula you should know. Now there are three special cases of this which I want you to realize. Okay, and I will show you all of them specifically for this formula. Say for example, for this inductance, this current happens to be constant. This current happens to be constant. Then di by dt will be 0. Di by dt will be 0. That means EMF will be 0. So, in such a scenario, you will notice that the EMF is going to be a big fat 0. So, this particular inductor will just behave like a simple wire. It will behave like a simple wire carrying that current, so that inductance has no role to play. It's not going to do anything. Okay, you are maintaining your current, you just be it. So, I'm just not doing anything. I'm just allowing the current to pass. You will not do only anything. But imagine this particular inductor encounters a current which is increasing. Here current increases. Imagine. If the current increases, 100% the EMF will be there and it will try to oppose that increase. So, you will feel as if there is a battery of EMF exactly this, which is trying to oppose that current. So, it will behave like a battery. So, it will behave. Here it was just behaving like a simple wire. Here it will behave like a battery which is opposing that increase. And if in that same inductor, you notice that this current is decreasing, let's say it decreases, then you will notice it will behave like a battery. It will behave like a battery which helps in the increase of the current, because the current is decreasing, it does not like it, it helps. Magnitude wise, that EMF is L di by dt. Remember that. So, EMF magnitude wise is simply L times di by dt. Direction is different. That's why that minus sign is coming. Wherever the change happens, exactly opposite is the EMF. Magnitude wise, it is still going to be L times di by dt. Is this absolutely clear, everybody? Yep. Amazing. So, that is what an inductor does. Now, we can find how much is this inductance very easily. And the most common example is of a coil, or basically of a solenoid basically. How much is the inductance of a solenoid? So, we all remember a solenoid. It was nothing but multiple coils wound together and in different planes. So, this was a solenoid, and I am interested to figure out how much is the self-inductance of that particular solenoid. Everybody with me? Let's try to find out. So, in order to figure that out, what we'll do, we'll assume that there is some current passing through that solenoid, and we recollect the formula of inductance and flux and current, which was phi is equal to Li. Okay, fair enough. So, somehow I want flux now. If I know current, if I know flux, I can get L, because phi is L into I. So, how do I get flux? So, take any one coil of that solenoid, any one such coil. You will notice any such coil has magnetic field passing through it because of the current which it has only generated throughout the solenoid. And this magnetic field, we all remember, is mu naught Ni inside a solenoid. Inside a solenoid. This is your uniform magnetic field inside a long solenoid. Hence, we can say that, sir, there is a magnetic flux which is created. So, how much is that flux in one such coil? So, flux in any one such coil will be field multiplied by area. That means it will be mu naught into small n I multiplied by the area of that particular cross section. Remember, we were discussing only one such coil. We are discussing only one such coil. But there will be so many such coils inside a solenoid. If the length of the solenoid is let's say L, I cannot use capital L because that is the symbol of inductance. So, I will use small l. So, in that length, How many such turns are there? We already know the answer to that question. We know the number of turns per unit length is the total turns upon the total length. So the total number of turns is small n multiplied by L. We already know this answer. This is nothing but total turns. This is nothing but total number of turns. This small n, if you remember, the same n we are using here, is how many turns are there per unit length. How many turns are there per unit length? So if I try to figure out how much is the total flux in the solenoid, you will see the total flux will be whatever flux you got for any one such coil multiplied by n, because there are n such turns. Each time it passes through, it generates the same flux. So this same flux will get repeated capital N number of times. Great. So let's substitute everything. Mu naught NIA. So mu naught is there, small n is there, I is there, A is there. Capital N is also there. So I'll put small n into L. So rearranging it, I'll get mu naught. N multiplied by n is n square. A is also there, L is also there. The only thing remaining is current, and this is flux. Guys, just compare this equation with phi. Just compare this equation with flux is equal to inductance multiplied by current. Immediately you will realize what the value of inductance is. It's everything except the current. Just compare, you will get the answer. So therefore, my inductance will be mu naught, permeability, multiplied by number of turns per unit length whole square into the area of cross section multiplied by the length of the solenoid. Please don't confuse between this L over here. This is inductance. This is length of the solenoid. Okay? Or else many times people end up cancelling both these L's for stupid reasons. It is a silly mistake there. Okay? Remember this formula. Mu naught n square AL. Correct. Live stars. Amazing. Hello Aryan. Very good. Good evening everyone. Amazing. Amazing. Perfect. Let's do some questions on inductance so that you will get an idea. This was mutual. No, I don't want mutual. Self-inductance. Let's do this first and then we'll go to more questions. The self-inductance of a long solenoid is L. If both length and number of turns are doubled, its self-inductance becomes. Come on, I want you to figure out this answer. Yeah, figure out this answer. Yes, come on guys, everybody, what's the answer? Pakka, C, sure? Alright, let's have a look whether you guys are right or wrong. Very bad, it's not C, it is B. The self-inductance is L. If both length and the number of turns are doubled, then the self-inductance becomes. I think you mistook number of turns for number of turns per unit length. So be careful. Capital L is mu naught n square A multiplied by L. Now be very careful over here. This is capital N, not small l, not small n, and this length is this small l only. Okay, there is no problem with that length part. Problem is with this n part. So we all know in order to get that n, we have to do this manipulation. Number of turns per unit length is n by L. N by L. This is whole square into A into L. So this will become mu naught n square A length divided by this is L square. L and L will cancel. So we'll get mu naught A, mu naught into A, n square is there and L is there. So from this you are seeing inductance is proportional to n square and inversely proportional to length. So notice what is happening. Number of turns are doubled. So the numerator is doubled, but you are squaring the term of n. You are also doubling the length. So the denominator is doubled. So 2 square by 2 means you are making it 2 times. So if the right hand side is made 2 times, it's obvious the left hand side will also be 2 times. Hence the answer is B. Everybody answered C because you thought this was the formula. So then you thought this has become double, so this will become 4 times. This also become double, means this has become 2 times. So 2 into 4, you thought it was, I don't know, maybe 8 times. That's why some people answered D also. And I don't know why you answered C though, because C, you have ignored the variation of length. So yes, D and C both are wrong. It is B answer. Okay. Hi Chandrasekhar. Welcome man. Welcome. Yeah, understood. This is a big catch. A lot of you made a big silly mistake. Let's do more questions now on this. If current of 2 milliamperes reverses in an inductor in 10 milliseconds producing 2 volts, find its inductance. That's the question. Let's try and solve this. Let's understand what is really happening. There is an inductor in which the current has reversed in 10 milliseconds and it has produced, as a matter of fact, 2 volts. Why it has produced? Because whenever you change current, it will oppose, and that opposition will come with induced EMF. So it has produced an induced EMF of 2 volts. How much is the inductance? So think, is there a formula for voltage, inductance, current, time? I think we just discovered it some time back. EMF magnitude wise is L times change of current by the time interval. So why not use that as it is? So the magnitude of my EMF is how much ever is the inductance upon how much ever current changed per unit time, and I am taking mod of it. So the magnitude is 2 volts. Inductance I do not know. How much is the change of current? Lot of people think, sir, 2 became 2 only. No sir, but direction is reversed, man. So actually it is 2 minus 2 milliamperes. Milli means 10 to the power negative 3. Whole thing divided by the time interval, which is delta t, which is 10 milliseconds again. So it is 10 to the power minus 3 here also. Do you understand why this minus has come? Direction reverses. Meaning if it was 2, that number 2 has now become minus 2. That is the meaning of it. So minus becomes plus. So this will become L multiplied by 2 plus 2 is 4 divided by 10. These two people got cancelled. 2 is there here also. So 1 will become L multiplied by 2 divided by 10. 2 and 4 got cancelled. 2 is remaining. So therefore 1 is equal to L multiplied by 1 by 5. Therefore my inductance will be 5 Henry. Inductance will be 5 Henry. Got it? No, not 10. Why are you guys giving wrong answers? Saroj, be careful. Little stars. No, it's not 10 Henry. It is 5 Henry. See where you guys made a mistake. Alright. So let's do another question coming up on your screen. And here it is. And one more thing is there. Next question. A coil produces a flux of 0.6 Webers for a current of 2 amperes. If now the current changes to 3 amperes, or let's say we take changes to 4 amperes in 0.1 second, find the EMF generated. Find the EMF which is generated. This is the question. So let's understand it step by step, whatever is given to us. A coil is producing a magnetic flux of 0.6 Webers when you pass some current. So if you have a coil and if I know it produces some flux for some current, immediately I can use flux is equal to inductance into current. Flux is 0.6, isn't it? Inductance I do not know. Current is 2 amperes. So my inductance will become 0.6 divided by 2. That means it is nothing but 0.3 Henry. So I have just got my inductance as 0.3 Henry. But what will I do with this Henry? Let's understand on the second part. Notice now the current changes to 4 amperes. In some time, find the EMF. I know there is a formula which says EMF which is developed is inductance multiplied by how much ever current you change per unit time. The inductance I know is 0.3. The current has changed to 4 amperes from 2. So the change will be 4 minus 2, correct? 4 minus 2. How much time? 0.1 second. Point decimal will go, so 3 will remain. 4 minus 2 is 2, so it will just become 6 volts. So 6 volts is the answer. Very good. Understood, my dear warriors? Pakka? Clear? That's how you can solve it. So these kind of questions you can definitely expect in inductors. Sometimes the questions can also involve Kirchhoff's law. How? Observe. This is 5 volts. There is some resistance of, let's say, 10 ohms given. The current which is going, let's say, is 2 amperes. Then what happens is there is an inductance which is given, and that inductance, I can take, let's say, 3 Henry. And this current is increasing at 0.5 amperes per second. Then you have some battery over here of, let's say, 6 volts, and then there is a point over here. The question is, if this voltage is, let's say, V1, how much is this voltage? Let's see how do we solve this particular question. This point has 5 volts, a resistor, inductor and a battery, and some another point where we want to figure out the voltage. If I logically think, I probably have to figure out how much are the voltages which are dropping or increasing across each device. Adding them up over the 5 volts will give me the voltage at this point. Maybe it drops here, maybe it drops here or increases here, maybe it drops or increases here. Whatever those changes are there, if I pile it up over 5 volts, I will get the total voltage at V1. So why not use Kirchhoff's law? But remember, Kirchhoff's law had taught you both ways. If you start at a point and come back at the same point, that's a different story, then the answer is 0. But if you start at a point and go to some other point, what you get is a voltage difference. So that's exactly what we are going to do. Arshad Singh, don't waste our time. Nobody is going to join your mission, Jeet, beat, nothing. Okay, so chill, calm down, watch this lecture. Okay, don't waste another's time. Your promotion is of no use, whatever batch, whatever you are coming from. So don't waste and spam your efforts. Okay. Now, here is the thing. Let's start. At this point, I have a voltage of 5 volts plus whatever voltage across the resistor, plus whatever voltage across inductor, plus whatever voltage across the battery. Eventually, I reach the other point. will be the voltage at the other point. This is the Kirchhoff's law in the other form which we have seen, when you do not come back to the same point, you are at some another point. Yes, Ganesh, whatever doubt you have, let me know. Let's start. First with the resistor. In the resistor, the current is going in the direction and I am also traveling in the same direction. So voltage will drop. Remember, in the same current direction, the voltage always drops because current in a resistor goes from high to low voltage. So you are dropping down the voltage. So the drop will be IR. Current is 2, resistance is 10. Then let's go to the inductor. Inductor says the current is increasing. So inductor will reply, oh wait a minute, you are increasing, I will oppose you. So the inductor will behave like a battery which is trying to oppose the change in the current. So what will happen? Again, because of that, I am going from the positive terminal to the negative terminal of this equivalent battery. So again, my voltage should reduce. So it will be minus L times L is 3 into di by dt, rate of change of current, which is basically 0.5. So over here, I have used current into resistance. Over here, I have used L times di by dt formula. This sign came not because of minus L di by dt sign. It came because current was increasing. If in the same question the current was decreasing, then this inductor will say, wait, I will help you. And then this side will be negative, that side will be positive. So that case, it will help my voltage increase. So I will put a positive sign. So it depends on this word over here. Next, I am going to a battery. The battery will say, oh, you are going from negative to positive. Increase the voltage by 6 volts. And finally, I land over here. So just you have to solve this, nothing else. So this will be 5 minus 20. 3 into 0.5, that's basically 1.5. And then you have plus 6 is equal to V1. Therefore, V1 will be, this is 5 plus 6, which is 11. 11 minus 20 is basically minus 9. And then you have minus 1.5. Therefore, this voltage will be minus 10.5 volts. That is the final answer. Minus 10.5 volts. How many of you got it? Very good, little stars. Finally, great. Amazing, Kanishk. You got it. Very nice. Very nice. Perfect. So these kind of questions also you can get. Now, one thing though, which is remaining, is the energy aspect of it. So for that, I'll make you visualize this way. If I have an inductor and I have some current passing through it, then this inductor will create its own magnetic field. We just saw it. Will create its own magnetic field. So there is magnetic energy which is stored in an inductor. Which is carrying some current. Inductor which is carrying some current. How much is this energy? I want to know. So remember, I told you inductor is like inertia. So it will behave like mass in mechanics. In fact, many of the formulas, whatever you learned back there in mechanics, still work here, guys. And many people get surprised when I show them this particular chart actually. So what is that chart? Let me show you. This will help you a lot. Okay, this will help you a lot. Observe. Let me show you in fact all the terms. So when you have mechanics on one side, usually you start mechanics with position, then you start with velocity, then you start with acceleration, isn't it? Then you slowly go to mass. Then what happens after mass? You go to, all right, one second, do one thing. This is electromagnetism. Now let me take duplicate. Okay. Then after this, let's say we talk about acceleration is done, mass is done. Okay, then we take force, right? Actually we'll do one thing, we'll take spring over here, spring. Then we will take damping, which you have learned in fluids, which is B. Then mass is also done, this is also done. Then we can take momentum. Then we can take momentum, which is P. Then we will take spring energy, U is equal to half kx square. Then we'll take kinetic energy, which is half mv square. Then we'll take oscillation time period, which is 2 pi under root m by k. Then I'm just going to compare, and you will be seeing that so many things are basically common. Then we can also take spring force. Spring force is equal to k multiplied by x. Then we will take, okay, for now this much is enough, then we'll see more. What happens in electromagnetism is that wherever you see x, if you replace it with q, which is basically your charge, it behaves very similar way. The equations are very similar. Wherever you see velocity, you replace it with dq by dt, which is rate of change of current. If you realize, this is nothing but dq by dt. Just like this velocity was nothing but rate of change of position. This acceleration was dv by dt. Here there is no term for acceleration. You just leave it as di by dt, which is rate of change of current. That's all. Mass, which is inertia, here it becomes inductance. This L stands for not angular momentum. This is inductance. It is electrical inertia. Spring in electromagnetism is like capacitance, guys. Just that it behaves like 1 by C. Just that it behaves like 1 upon capacitance, or capacitance is 1 upon spring constant. Wherever you see K, replace it with 1 by C. If you see C, replace it with 1 by K. Damping is like resistance of an electrical circuit. Momentum is like flux. Momentum is like flux. Phi is equal to L into I. Notice what I had just told. P is equal to mv. M is mass, inductance. Velocity is current. Momentum is flux. Observe carefully. Here only I have mentioned velocity is exactly like current. Mass is just like inductance. So momentum being mass into velocity, if I take the product of inductance into current, it is basically like flux only. So flux in electromagnetism is how much flux is flowing through a coil. It's a momentum in mechanics. Are you seeing the similarities, everyone? Now you will see even more. Now you will start getting surprised. Observe this. In mechanics, spring energy is half kx square. In electromagnetism, the energy stored in a capacitor. This is energy stored in a capacitor. Remember, this was a spring potential energy. This was spring potential energy. Would be, see, wherever you see K, what did I tell you? Wherever you see K, replace it with 1 by C. If you see C, replace it with 1 by K. So notice what will happen. Instead of K, you put 1 by C. So C will come below. And what you do now? X, what is X? Position. What is position? Position is like charge. Exactly, just put charge over here. Q square by 2C. That's why I said charge is like position. So half kx square becomes q square by 2c, which is exactly our formula. This is our kinetic energy of a mass. What will happen? This will now replaced by half into, instead of mass, you will have inductance. Instead of velocity, what did I tell you? Velocity is exactly like current, isn't it? So you will see it will be replaced with current, and this is exactly the energy stored in an inductor. Exactly the energy stored in an inductor. So that's why when I said magnetic energy is stored inside this inductor, the answer for this will be simply half L I square, nothing else. It will be just half L I square, guys. Okay. So just by simple comparison also you can see. This is a spring mass system which is oscillating. This is a spring mass system which is oscillating. You will see that if you take, instead of spring, what do you take? A capacitor. Instead of mass, what do you take? An inductor. You will notice the charge will go back and forth. Just like this mass will move, change its position back and forth, the charge will keep oscillating back and forth, and the time period of this oscillation will be 2 pi. Instead of mass, I am going to put inductance, and wherever I see K, I should put 1 by C. That means the reciprocal will come, so capacitance will go on the top. So 2 pi root of LC. That will be the time period of oscillation if you take a charge and leave it on a capacitor. The capacitor will give it to inductor. Inductor will shift it to other side. Again the capacitor will get charged. Again it will shift it to the other side. The charge keeps oscillating back and forth with this particular time period. Okay? Is this crazy? Yes or no? Now, I'll still show you more. We are not done yet. Spring force is Kx. What we'll do? This K is nothing but 1 by C. Spring constant is like 1 by capacitance. X is just like Q. This force is like voltage, or any force is basically like EMF. Wherever you see voltage and EMF, that can be replaced with force. Yes, so if you are wondering what is force in electromagnetism, it is either voltage or basically EMF, basically, right? So this is volts, voltage. Here F stands for your force. Notice this is a standard expression. Q is equal to capacitance into voltage. Q is equal to CV. We know this, right? Okay. Now I'll show you one more thing. If I say damping force, F damping force, this is nothing but B into V. B into V. So in fluids or in SHM, you would have seen this. There is a damping force. Any body which is moving with speed V, it experiences a damping force. Notice how it happens in electromagnetism. This B I just mentioned, it is like resistance over here. Damping is like resistance. So you will have resistance over here. Velocity is basically like current. Velocity is basically like current. Force is like voltage. V is equal to IR. That is Ohm's law. That is your Ohm's law. So damping force is BV, is Ohm's law in electromagnetism. It's very funny, guys. I mean, like, look at it. Just look at it. It's crazy, isn't it? Yeah. Okay, I'll show you one more thing that will also blow your mind. Newton's law. Okay, F is equal to ma, guys. Newton's law. F is equal to ma. Fair enough. Let me go on to this side. What is equivalent of mass? It is inductance. What is acceleration? Acceleration is di by dt. There is no term which is defined. We just call it a rate of change of current, isn't it? We just call it a rate of change of current. We don't have a special name for it, just rate of change of current. So instead of acceleration, why don't we put di by dt? What do you get on the left hand side? Force equivalent is voltage. Exactly what we are expecting. Voltage across the inductor is L di by dt. Yes, we know that. Voltage across the inductor is L di by dt. So every formula works. Isn't it crazy? Loved it? So you know mechanics, you know electromagnetism formulas indirectly. You know kinematics, linear motion, you know circular motion and rotational motion, because there also the formulas are similar. Yeah. So that is the comparison table which everybody must know. Okay. So from that we can see anything which has a magnetic field will store magnetic energy within that. Will store magnetic energy within that. Now you can figure out how much is this magnetic energy per unit volume. That is a very important term. So inside that inductor, this magnetic field is there. I will take my own sweet volume, which I call it as unit volume. This is my volume. And I want to know what is the magnetic energy which is stored in that inductor. Remember that inductor was there. I'm not showing the complete inductor. Just visualize this. I have missed that middle part deliberately to show there is magnetic energy stored inside that inductor. So I want to know how much is the magnetic energy per unit volume. The magnetic energy density, basically. Magnetic energy density. The symbol for that is density, but it is magnetic in nature, so I'll put rho B. That is how much ever energy stored upon how much ever volume is there. How much is that energy stored? We just figured it out over here, and I told you it is half Li square. That magnetic energy is nothing but half Li square. How much is the volume? The volume of that entire inductor will be area of cross section multiplied by length. Okay. But wait a minute. I know what is the inductance. Inductance of a solenoid, we just calculated it, mu naught n square Al. Mu naught n square Al. So why not substitute that? Mu naught n square area multiplied by length. This current still stays as it is. Whole thing divided by area and length. A couple of them will cancel, maybe, I guess, like this area, this length, this length. Nothing else is cancelling out. So my magnetic energy density turns out to be half is there, mu naught is there, n square and I square is also there, and one last thing, no, nothing, no last thing, that's all. I'm not liking this. What I will do, deliberately I will square mu naught. So to preserve the equality, I have to divide with mu naught, because only one mu naught was there. Now I realize one interesting thing. This mu naught Ni, if clubbed together and then squared, I know what is this mu naught Ni. What is this mu naught Ni? It is nothing but the magnetic field. Oh, crazy. So we got the magnetic energy density as B square by 2 mu naught. Now just compare this for a moment with electrical energy density. With electrical energy density. What was it? Half epsilon naught electric field square. Very similar. And I told you this even in magnetic fields. The formulas are very identical even in electricity and in magnetism. Wherever you see electric field, it will get replaced by magnetic field. Half is there, half is there. But if you see mu naught, it will be replaced with 1 by epsilon. Or if you see epsilon, it will be replaced by 1 by mu naught. So that's why even in the field formula, in electrostatics, epsilon used to come below. 1 by 4 pi epsilon naught, this. Field, sigma by 2 epsilon. Epsilon was below. But in magnetic field, every time mu naught is on the top. Mu naught I by 2r, mu naught I by 2 pi r, mu naught something on the top. So it's always reciprocal. Understood? So that's how you can easily remember this formula. If you ask me the units of it, it's the same, guys. It's energy density at the end of the day. So it will still be how many ever joules of energy stored per meter cube. Joules per meter cube is the unit of magnetic energy density. Clear, everyone? B square by 2 mu naught. Alright, so very, very straightforward to remember this formula. Great. So let's do a question maybe on this. a current of 2 amperes draws a power of let's say 16 watts across inductor in steady state. Now the current is dropped, or basically, one second, this is there, the current is stopped and some heat is generated in that inductance of 3 Henry. Find number 1, resistance of that particular coil. Number 2, whatever that heat was generated. So very good question, because it clubs 2 concepts or more here. We need to understand what is really happening. You are passing a constant, steady means constant or constant means steady, of 2 amperes, and power is being delivered to the inductor. But this is against my belief that inductor will always allow the current as it is. It behaves like a wire. How on earth is this inductor causing this power to be delivered to itself? That hint comes from the question asked. Coil resistance. Oh, the coil of that inductor is made of a wire. So obviously it might have some resistance which you used to ignore maybe. This tells me even an inductor can have resistance of itself, which is called internal resistance or coil resistance. Just like a battery can have its own internal resistance. This is just like a battery's internal resistance concept. So a real inductor, because it has some internal coil resistance is just like saying you have a regular ideal inductor and just some resistance beside it. Now when you visualize it this way, the problem starts to make sense. So let's visualize. A current of 2 amperes is passing through this inductor and a power is delivered. So that power is not obviously going to the inductor, it is going to the resistance. So the resistance is losing it as heat, the internal resistance, and that is given, my dear friend, as 16 watts, and this current is given to be how much? 2 amperes. Oh, so can I not say power is I squared into R, and this 16 is equal to 2 square multiplied by the resistance. So therefore 16 is equal to 4R, therefore R is equal to 16 by 4. So R is 4 ohms, which is the coil resistance. This takes care of the first part. So when you split it into 2 parts, inductance ideal and resistance internal, it looks much easier. Now coming to the second part, the heat. What happens when the current is stopped? The moment the current is stopped, whatever energy was stored immediately will start going away. Where? In that coil, in that resistance. So energy stored will be completely going into heat. So whatever heat has been generated is coming from the energy stored inside the inductor. And how much is the energy stored in the inductor? It is half Li square. So what is the value of the inductance? It's mentioned as 3. What is the current? It is 2. So 2 and 2 will cancel. So 3 into 2 will be there. So it will be 6 joules. So the heat which is generated is 6 joules. Got it? Yeah. No, this is not exactly current electricity, but the concept of current electricity is used, man. Shubham. Current electricity concepts will be used everywhere, whether it is inductance, capacitors, everywhere. So these kind of questions you can expect, guys. So we have solved couple of questions from inductors and inductance. Now let's go to mutual inductance. There is a small part of it which we need to do. So mutual inductance. If you have a coil carrying some current, this coil I call it as the primary coil. This primary coil is placed near some another coil. This coil I will call it secondary coil. I am not passing any current through the secondary, I am just leaving it as it is. Because the primary coil has an actual current through it, it will generate a magnetic field, some of which will pass through the secondary coil. Not all, some of it. So whatever passes through the secondary coil will create some flux in the secondary. So if the secondary, why is it called secondary? Because the primary is the first one to be carrying the current. The next coil which is impacted, that's why I am calling it as the secondary. So there is some flux in the secondary coil. There is some magnetic flux. So some of the magnetic flux in the secondary coil, I can call it as phi 2. That will be proportional to how much ever current I am passing in the primary coil. Whatever current I am passing over here, because of that magnetic field is generated. If I increase the current, more field, more flux, that's why phi will increase. So it is proportional to that. So if I rewrite it without the proportionality symbol, I'll just put phi 2, then there will be equal to, then I will just write down a term called as M, which is called mutual inductance, because it is between them, it's not of the coil itself. It is a mutual inductance. So this M is then called mutual inductance. Same unit, guys. It is also measured in Henry only, which is obviously Weber per ampere. Also, it depends on both coils. It depends on both the coils, how far they are, how big they are, how many turns are there. All of those geometrical parameters will decide that mutual inductance. So this is what the formula for mutual inductance is. Now you might be wondering, I know, sir, what if I pass current through this and then I see the effect on this? Will the mutual inductance be different? The answer is no. Whether you make this coil primary or this coil primary doesn't matter. Every time the mutual inductance is the same. So this M doesn't depend on, so M is literally mutual. M doesn't depend on which coil actually is primary, which coil is primary or secondary. If this is primary, this is secondary, or this is primary, this is secondary, doesn't matter, still it will be the same. Okay, this is a very important parameter of M which you need to know. Now, same way, I can say that if I have this primary coil, I am passing some current I1 and I am placing a coil beside of it, it is experiencing some of the magnetic field, so it will also encounter some EMF inside of it because some flux will change. So this is the EMF generated, or I would say induced, in the secondary coil, by Faraday's law. That EMF will be negative rate of change of the flux inside that secondary coil. But how much is the flux, guys? How much is that flux in the secondary coil? We just saw it is m times of I. It is just nothing but m times of I. So very similar looking formula, minus m di by dt. That is the EMF of it. That is basically the EMF of it. That's it. Straight and simple. Similarly, you can also figure out how much is the mutual inductance for two concentric coils. Imagine something like this. There is a solenoid inside a solenoid. There is a solenoid inside a solenoid. So this is the solenoid which is inside. This is the solenoid which is outside. Okay, this is the outside solenoid. The outside one, I call it primary solenoid. That primary solenoid has some current I1 passing through it. So that primary solenoid, what will it do? It will generate a magnetic field. So whatever is the magnetic field inside the bigger solenoid, bigger or basically outer solenoid, will be given by magnetic field will be mu naught number of turns per unit length into the length of the solenoid. Whatever is the number of turns per unit length of that outer solenoid multiplied by the length of it. Fair enough. Out of that magnetic field, what will happen? Every coil inside, which is this yellow one, will experience a flux. So the flux in each coil, each of that inner coil will be how much? Whatever is this magnetic field B1 multiplied by whatever is the area of that small coil. Whatever is that area of that small coil that you see over here, that area I will call it as, let's say, small a. You can call it big A also, doesn't matter. That field we already know is mu naught N1L into this small a. Great. So can we now figure out how much is the total flux? How much is the total flux in the secondary inner coil? The inner coil is the secondary. The inner coil is basically my secondary coil. So that flux in the secondary coil will be whatever I get in each of these coils, which is mu naught N1L into A. It was I, no guys. Why did I write L? My bad. Sorry guys. Happens. Long lecture. This was supposed to be current. That's what I was wondering. Something went wrong. This was supposed to be current. Mu naught N1. What is this? I1. Mu naught N1 I1 multiplied by your A was there. Multiplied by how many ever turns that inner coil has. Multiplied by how many ever turns the inner coil, which is the secondary coil, has. That will be mu naught N1 I1 A. Number of turns is number of turns per unit length multiplied by the length. Okay, so I can rewrite it like this: mu naught N1 N2 A L into current in the primary. Now compare this with flux in the secondary is mutual inductance into current in the primary. Simple comparison is enough. Immediately you get the answer for mutual inductance. The mutual inductance comes out to be mu naught small n1 small n2 area of the smaller coil into the total length. That's it. That is the answer, guys. Compare this with a normal solenoid's formula, a regular solenoid's formula. You will see a lot of similarities. Mu naught n square al. There was only single area, single length and single number of turns. So n square was there. That n square now, instead of mu naught n square al, has just been converted into n1, n2 and smaller area, never the bigger area. Okay, so usually students get confused, is it big area or small area? It's always the smaller area of the coil which is there. Cool? Alright. Is it true Faraday has no mathematical background? Not really, but it's said that Faraday's laws were, or rather Faraday was more fascinated with experiments and physics than mathematics. So Faraday always gave those laws which told about, okay, magnetic flux changing produces electricity, how fast it is, but he never actually formulated the mathematical expressions properly. It was Maxwell who used Lenz's law, Faraday's law and other concepts of electromagnetism and then gave those formal integral and derivatives equation. And Maxwell was very opposite of, very behavior wise and thought process wise, exactly opposite of all these other scientists. He was a pure mathematics oriented guy. You should love mathematics, so that's why his equations are with, you know, all those integrals, derivatives, curls and all those things. So that's a ideological difference. Notes you will get it from the PW app, man. Okay, great. So let's do a question on this. Two coils have mutual inductance. Current in the primary is so and so. The peak EMF induced in the secondaries. Okay, not bad. EMF in the secondary. EMF for mutual inductance is m di by dt. Mutual inductance is 0.005 Henry. Derivative of current means d by dt of this entire thing, which is 10 sine of 100 pi and t. This 0.005 is basically 5 divided by 1000, nothing else. When I take derivative, by the way, this number 10 will come outside. Sine will become cos. This will become 100 pi and t. In even this 100 pi has to come outside, correct? Because of chain rule. Sine of ax's derivative is cos ax with a outside. So a cos ax is the derivative. So a comes outside. As you can see, these three zeros cancel and we are left with 5 pi cos 100 pi and t. Simple mathematics says that this cos term has a max value of 1. So naturally, when I want this EMF's max value, it will be obviously this, because this number is 1 into this. So 5 pi should be the maximum value, which is option number C, guys. Is that right? Option C is the correct answer. Okay. Very, very important. Great. Now, this sometimes what they will tell you, okay, we are combining inductors and all of that. So those kind of questions can also come, but before, I think combination of inductors is, that is the next part. Okay. So we don't need these slides anymore. Cool. Now let's go to the last few things, LR and combination of inductors. See, if you take inductor like this and like this, they are basically in series. And if you take an inductor side by side to each other, they are obviously in parallel. Any such inductors, one after the other or side by side, which is series or parallel, can be combined into a single inductor, like this is LS and this is also a single inductor. S stands for series here. Here this will be LP, P stands for parallel. The formula for LS and LP is as follows. For series, just add them just like your resistances. Don't worry, it is not like capacitors which are very weird. And for parallel, again same like resistors only, it will be 1 by LP will be 1 by L1 plus 1 by L2. So they behave very much similar to your resistors. Behave very much similar to your resistors. Okay, as simple as that. Now sometimes what happens, oh by the way, these formulas are valid provided this inductor does not affect this does not affect this, or this does not affect this, or this does not affect it. We have ignored their mutual inductances. That's a very important statement that I am making here. Ignore mutual inductance since they are far away from each other. Otherwise, this field will affect this will affect this, and it will create a mutual effect. And when that mutual effect has to be considered, then you will see the formula changes slightly. So right now they are close by to each other. So if this is L1 and this is L2, then this creating a magnetic field will affect this will affect this. So there will be a change now in the formula. Now if they are close, it will be L1 plus L2 minus basically 2m. So there is a small change. There is a small change which comes when there is closeness in them. So when they are close by, the mutual effect, the mutual inductance will dominate as well, which is M, and it will also change the effective inductance. This is very, very important. But you will see in some books or in some questions, there are some another weird kind of questions where you take this inductor like this and like that. So what you have done, the second inductor, you have flipped its terminals. So ideally the current would have just gone like this, right? Current was just going like this, like this, like this. In this second scenario, it was going like this. Now it is going like this, and then it is coming out. In such a case, the formula is slightly different. It is the L effective will be L1 plus L2 plus 2m. Plus 2m. Yes. Yeah? Everybody with me? Everybody? Okay, very, very important. Very, very important, guys. Cool? Pakka? Yeah? Very good, very good, very good. Many of you, yes. Plus 2m or minus 2m? Well, you are right in a way. No, it is minus 2m only, man. It is not plus 2m. Plus 2m comes if they are no, you are right. Actually, 1 second. Yeah, all is well. Yeah. Magnetic fields. Yeah. I think you are right over here. I think this was supposed to be plus and this was supposed to be minus, man. This is plus and this is minus. Yeah, this is plus and this is minus. Just let me do one thing. Let me just check once in my book also. Just give me a second so that we are not learning the wrong thing. Yes, guys, this is the correct formula. I'm so sorry. Earlier I put this as minus and this as plus. This is the right formula. Okay. Yeah. This is right. So when you have two inductors in this way, it will be plus 2m. They will add up their mutual inductance, and when it is exactly like this, then it will be subtracting their inductances. So this will be L1 and this is basically L2. Okay. Fine. Then another thing is, if you have an inductor, say L1, and another inductor over it, okay, another, just showing like this, another inductor L2, then these two inductors will have their own mutual inductance. Yeah. Okay. Yes. So do you know Hindi? Yes, man, I know Hindi. Now these two inductors will have their own mutual inductance. Now this particular mutual inductance, right? This particular mutual inductance is given by some number k multiplied by root of L1 and L2. This k over here is called as coupling factor. And this coupling factor has a least value of 0 and a highest value of 1. It can't go more than 1, it can't go less than 0. So coupling factor basically tells me how much of their inductances are translating or getting converted into mutual. It means how well they are coupled. If these two inductors are very far away, then they will not exert any mutual inductance on each other. So the coupling factor will be negligible. But these coils are intertwined, and whatever flux goes through this also goes through that. Whatever goes through that will go through this. Then they are having maximum coupling between them. So that factor comes out to be 1. So that is basically your coupling factor. Great. So these concepts of combination of inductors are something which you should know. First being in series, it is L1 plus L2. Second being in parallel, it is just like resistors, add the reciprocals. If you consider the mutual inductance when they are close by, then it is plus 2m or minus 2m, depending on their arrangement, nothing else. And lastly, the mutual coefficient of inductance will be a number which is less than 1 into the product of the roots of the inductances. That number is called coupling factor. The last part is the growth and the decay of current in an inductive and resistance circuit. So if you take an inductor along with a resistance, there is a switch, let's say, and you take a battery, this is your EMF, this is resistance, this is inductance. You turn the switch on at t is equal to 0. You will see that there will be a current in this circuit, and the current will grow, and the current grows till it saturates, it reaches a final value, and when it reaches a final value, it looks something like this. The current will no longer change. This inductor will have constant current, so it will behave like a simple wire. This is the final current which will go into it, so I can call it capital I also. This is your resistance, let's say. This is your battery. And this current undoubtedly will just be E divided by R. It can't go more than this. This is the final current, because this will behave like a wire, and it is a simple circuit with a resistance and a battery. So current will be voltage by resistance. So it will behave like a wire. This is after a long time. And this is called as your steady state. This is called as your steady state of that inductor. So when you turn on the switch, the EMF will supply the current, inductor will resist that change. So it will take some time for the current to finally reach this saturation or steady state value, and eventually it will reach that value. If you look at the graph of this, it looks something like this. The graph of how the current will change with time, The maximum current that you will reach will be I, but that will be after a long time, that is capital I. But other times the current will be growing like this, slowly. Whenever you turn on the switch, it will go like this. Asymptotically, it will reach the maximum value slowly after a long time. And this is an exponential, you can say, kind of reach which is happening over here. So this is how the current will change with respect to time. Now, if you ask me the equation, it will look very similar to the equation of charging of a capacitor. This is also like growth of current in an inductor. So very similar looking formula. So you will see it will be final maximum current into 1 minus e raised to minus RT divided by L. This is the formula. This is the formula for the growth of current in a LR circuit. E is that exponential part, R is resistance, L is inductance. So those factors will decide how quickly it is rising. Now, this particular I over here is nothing but E by R. So if you want, you can use E by R. But if you want to write it in a slightly better way, we usually write maximum current. Then we also write 1 minus e raised to minus t by another number called as tau. This is a much better way of remembering things. So usually we remember it like this, where my tau is called as the time constant of the LR circuit. This is nothing but time constant of the LR circuit, which has the value of L by R. Like you had time constant as RC, this is nothing but L by R. Sir, so then what is this time constant achieving basically? So if you actually ask me, what is this particular time constant achieving, which is L by R? We get an idea of when the current reaches a certain value. So if I plot where the time constant is over here, maybe it's like this, and I see what is the current at that particular time, will be something like this. So we can figure it out, it's not that difficult. So current will be maximum current into 1 minus e to the power, my time is the time constant, so it will be e raised to minus 1. E raised to minus 1 is a very specific value, guys. It is 0.37. You should remember that value. It's better. And 1 minus 0.37 is 0.63. So this will be 0.63 multiplied by the total current or the final current, which means it will be 63% of the final value. So it has almost reached 63%. You wait for 2 to 3 time constants, it would have, even 4 time constants is a decent amount. It would have reached almost more than 95-97%, which means it has almost reached steady state. So this time constant gives me an idea of roughly how much time it takes to reach 63% of the final value. So if I wait for 4 to 5 time constants, I have almost reached steady state, because it's almost like 98-99%. Got it? This concept was also there in RC circuits. Over there it was Q is equal to CV 1 minus e to the power minus T by RC. Here it is 1 minus e to the power minus RT by L, where L by R is your time constant. Okay. What is E? E is your exponential value, guys. Yeah. L is what is L? L is inductance. No? L is inductance. E is your standard value. So you should at least know this number. 1 by E is 0.37 and E is basically 2.7 approximately. So you should know these values by heart, will be helpful to get decent values. Now, the exact opposite of it is when you have decay. But before going to decay, one specific thing I want you to see. We will take two special cases over here in the growth only. Current is I 1 minus e to the power minus RT by L. Take two specific cases. First case, time is equal to 0. If I put time is equal to 0, I naught will be I 1 minus e to the power minus 0. Okay, so which means I e raised to 0 minus 0 is the same, it is just 1. So basically the current comes out to be 0. Okay, let's keep it on the sidelines. Now let's take the second case. When time tends to infinity, then what happens? The current becomes I into 1 minus e to the power minus infinity. E to the power minus infinity means 1 by a very large number. 1 by a very large number means almost 0, which means the current will almost become I only. So what this tells me is that when you just connect an inductor, t is equal to 0 means what? You have just connected an inductor. The inductor behaves as if it is not allowing only any current. So you will notice it behaves like an open circuit. It doesn't allow only any current. But the moment an inductor is reaching a steady value, that is after a long time, if you relieve it, then the same inductor behaves as if it's just a closed circuit or just basically a wire. So this is the behavior of an inductor when it is just connected versus just closed. Now I want you to recollect from our RC circuits lecture, how was the behavior of a capacitor? If you try and recollect the behavior of a capacitor, you will realize a capacitor, when it is just connected, actually it behaves like a wire. It is exactly opposite. Whereas a capacitor which has been in the circuit for a long time and reached its steady value, that one behaves like an open circuit. So the behaviors are quite opposite for inductors and capacitors in a resistive circuit, when just connected versus connected for a long time. Okay, so keep these things in mind. JEE advanced questions will use these concepts. Now let's go to the last part, which is decay of current. So you have an inductor, and what happens is it has some current passing through it, and you allow that current to decay through this resistance. So this is the current, this is the inductor. So it so happens that initially, if you notice, initially the inductor had a good amount of current. This is at t is equal to 0 initially, but eventually everything will be lost out, and after a long time all the current will decay, and you wait for a long time, yes, the current will be 0 amperes. The current will be 0 ampere after a long time. So the graph will look something like this. This is my time expression. This is my current. This is 0. So I will start from I and I will slowly reduce capital I, and I will slowly go down like this. This was my initial value, which is capital I. Finally, I will reach almost negligible value after a very long time. So this equation, you can predict now how it will look like. go back slightly. Whatever equation you got, it's very similar to charging of a capacitor. So discharging of a capacitor, how was the equation? It will look very similar. So you will not get 1 minus e, you will just get e raised to some negative power. So it will be whatever is my initial current, e raised to minus RT by L, but usually we prefer writing in terms of time constant. So minus T by tau. Minus T by tau also you can write. Tau is the time constant of the LR circuit. So my time constant tau, which is L by R. If you wait for one time constant, what exactly happens? So it will be somewhere here. And now if I see what is the current that I am getting after one time constant. So just put the value of time as tau. So I into e to the power minus tau by tau. So it will become I into e raised to minus 1, which is I into 1 by e, which is 0.37. So this basically means my current has now become 37% of the original value, or 63% has gone away. So now it is 37% of initial value. Hardly 37% is there. So if you wait for 4 or 5 time constant, that 37 will become slowly 14, 15%, 10%, 5%, 1%, hardly anything will be there. So again, the time constant gives me the idea of how long does the inductor take to decay the current. You just wait for 4 to 5 time constants, enough. That's the current has gone away almost to 0 amperes. Cool. So this was the decay of the current. Great. So I think we have covered literally everything. We'll just do 2 questions on this so that you know how to solve the questions. There is a coil which is connected. The time taken to reach half its steady state value is how much? If I make you visualize it, it will be like this. It will go up like this, right? I want to reach 50% basically. I want to reach 50% of the total current. Question is, how much time will it take? How much time will it take to go to 50%? We know 37%, but we don't know 50%. So we'll go with the generic equation for charging, which is EMF by resistance 1 minus e to the power minus RT by L. Why I'm using RT by L? Because everything is given, L, R and all of that. Now 50% of its steady value. See guys, this E by R which is there, right? Whatever you see, this is exactly the steady state current. So if I want to reach half of it, that means half of E by R. It is half of E by R. Oh, so I will put half E by R over here. This is also E by R. So now rest of the things as it is only. 1 minus e to the power minus RT by L. E by R will cancel. Do you understand why I did this? E by R is the final value which it reaches, steady value. So I want to reach half of it, that means 50% of it. So that means half of the final value which was E by R. Remember, this total current which you get finally is E by R. Okay. So if that cancels, I will have half is equal to 1 minus e to the power minus RT by L. Bring this on this side. So e to the power minus RT by L will be 1 as it is. Half goes on the other side. Bring this term down. So 1 by e to the power minus RT, sorry, this will become plus RT by L will be 1 minus half is just half. Shift it on the top. So therefore, or cross multiply, whatever you want to say. So e to the power plus RT by L will be just the number 2. Taking logarithms concept, so I will see log of 2 to the base e will be RT by L. Therefore, time will be L by R log of 2 to the base e. I think that is what now we want, the time. Inductance is 300 millihenry, meaning it is 0.3 Henry. This number is just 0.3. Resistance is 2. Log is nothing but ln. So it is ln2. So 0.3 means 3 by 10, which is basically you can say 3 by 10, or this is 1.5, so 0.15. Yeah, this is 0.15 ln 2. This is the value of time, but answer will be in seconds. So 0.15 is the answer, which is option number A. Perfect. There you go. So these questions are pure mathematical and solving wise. So if you know the formula, it becomes easy, or else it will look little difficult. Okay, cool. Understood. Let's go to the last question then, coming up on your screen, and here it is. What is it? What is it? What is it? A voltage is applied. The voltage is this much at 0. It drops to 5 at 20 milliseconds. What's the time constant of the circuit? Great. How do I find time constant of the circuit if voltage is given at 20 milliseconds, right? You might be wondering. So let's think about it. If I figure out my current versus time graph, this is current versus time. The inductor voltage is 20 volts at t is equal to 0, and it drops. So, okay, it is a decay circuit because you are leaving that inductor, so it is slowly decaying. If current changes, the rate of change of current is the voltage. Oh, perfect. So I can get the voltage by differentiating current. So my voltage across the inductor, recollect, was actually L times di by dt. So I just need to take L and take derivative of the current, and the current is that whole big expression which was original current into e raised to minus RT by L, minus RT by L. Great. So I have to take this whole thing's derivative. So I can be taken outside, so it will become L multiplied by I. E raised to x's derivative is e raised to x only, so minus RT by L. But it is not x, it is some ax form, so that a will come outside. So I will again get minus R by L over here. Great. So I am left with minus, actually there is a minus sign here. So if you use that minus sign, what happens? Eventually this minus and this minus will cancel, it will become plus. So if you go systematically or methodically. But anyways, I am interested more in the magnitude part. LL got cancelled, negative got cancelled. So plus I into e to the power minus RT by L is the voltage across the inductor. So you can see voltage depends on this number. This is a constant. So if I just happen to take voltage at 0 versus voltage at 20 milliseconds, I and I will get cancelled anyways. It is this number which will matter. So minus R multiplied by 0 by L divided by e raised to minus R multiplied by 20 milliseconds by L. That's what it will be. Is that right? So yes. Perfect. Now this number V0 by V20. V0 initial voltage is 20. Final voltage at 20 milliseconds is basically 5. I got cancelled. This will become e raised to 0. This will become e raised to minus this R and L I can replace with time constant only, no? So forget it. So minus 20 by tau, because L by R is time constant. Great. So let's solve this now. What do we get? 20 by 5 means it will be 4. E raised to 0 means it will be 1. Okay. And this will be e raised to minus 20 by tau. Okay. Bring it on the other side. So 1 by 4 will be e raised to minus will become plus 20 by tau. Taking logarithms, I will get log of 1 by 4 to the base e is 20 by t. Okay, so log of 1 by 4 is there. Log of 4, I can see already things are there. Yep, that's right. Log of 4 is there. So I can take it on the upper side if you want, or what do we want? Time constant, right? So take time constant over here, 20 will be there, and we'll have log of 1 by 4 over here, but you can also write this as 20 by minus log of 4 like this, but I don't know why this minus sign has come. Have we missed out on some number over here? Just see if you have missed out on some number. This should not come minus. Let's just check. Minus RT by L. RT by L. Okay. So time is 20 milliseconds. Fine. Everything I'm doing in milliseconds only. So this will be like that. Great. 5 volts at 20 milliseconds. 5 and this will come together. Correct. So 20 by 5 is 4. This will remain here when it goes on the... I made a mistake here, guys. Sorry. When I had to shift over here, I made a mistake. So when I had to take it, I deliberately shifted that 4 also, was not needed. Yeah. So now it's fine. It's fine. So this will become log of 4 to the base e will be nothing but 20 by time. Great. So my time constant will be 20 by log of 4 to the base e. So 20 by log of 4 to the base e, that will be the answer, which is obviously option number B. Yeah, that is correct. Yeah, that is the right answer. Great. Yes, amazing. So that was our last question for today. I hope you enjoyed the questions. I hope you enjoyed the theory. We have done everything in detail. We have done all the formulas for inductors, combination of inductors, coupling, mutual inductance, self-inductance, time varying magnetic fields, the generic formula of motional EMF, Faraday's and Lenz's law, right? Everything, guys. We have literally covered the entire chapter in this long, beautiful class. So take care. Thank you so much. I would love to see your comments. There are few questions which I have given as homework in the middle of the session. So if you are watching the session completely, you will find that homework questions. Answers will be there in the PDF, which will be uploaded within the app. So make sure you are downloading the PW app and checking the PDFs and solutions there. Okay, great. All right. Have a great time. Take care. Bye bye.